Bun găsit la emisiunea Știință și Cunoaștere. Vă spuneam nu cu mult timp în urmă faptul că pe parcursul anului 2013 am avut ocazia de a realiza mai multe interviuri cu invitați din străinătate. Aș putea spune chiar fără să exagerez că au fost câțiva dintre cei mai renumiți din lume, cercetători, profesori și filozofi cu studii și calități excepționale. Într-un anume fel, fiecare nouă emisiune a devenit ca o carte de vizită, care ulterior mi-a permis să intru în legătură cu personalități de notorietate pe plan internațional. Dar acest lucru s-a întâmplat nu doar prin intermediul internetului, ci și cu ajutorul unor împrejurări foarte interesante, deoarece, de exemplu, în cursul lunii august a sosit la Cluj unul dintre cei mai de seamă matematicieni de la Institutul de Tehnologie din Massachusetts, profesorul MaxTegmark, având preocupări cu totul speciale în ceea ce privește matematica, deoarece, așa după cum veți putea afla peste câteva momente, domnia sa a publicat recent o carte care se numește Universul matematic. Fiind anunțat de prezența sa la Cluj, am reușit să programăm o sesiune întreagă de 3 ore de discuții chiar la sediul TVR Cluj și țin neapărat să mulțumesc echipei tehnice pentru ajutorul acordat într-o perioadă extrem de aglomerată care a fost luna august. Hello and welcome for the first time in Science and Knowledge on TVR Cluj in Romania.
Mulțumesc foarte mult! Vorbesc puțin românește, nu foarte bine, so maybe we should continue in English.
Yes, I am happy that you know something about us and about our language. Is it your first visit?
It's actually my third visit. I was here last summer also to visit my wife, whose relatives. I have the good taste of marrying a Transylvanian, Mihaela Kita, and I also was here in 1990.
In 1990, so long ago.
Yeah, it was very interesting to compare Romania during the Mineriad, right after the revolution, with Romania now, and it makes me very happy to see how much better things have become.
Well, very nice to have you here on our studio for a very fascinating talk about cosmology. It is for the first time when we have this subject in our program, Science and Knowledge, because there are so few specialists who knows cosmology and who can explain it for the untrained public. So we are now getting into the subject. In this program we will debate the part 1 from cosmology, which is about a short history of our universe. What are we referring to when we say our universe?
When we talk today as scientists about our universe, what we mean is basically this: the spherical region of space from which light has had time to reach us so far during the approximately 14 billion years since our Big Bang. So, in other words, there is probably more space outside of this, but we can't see it yet because the light from farther away has not had time to come to Earth yet. And this is what we mean by our universe. And our great challenge as scientists is to try to understand what is inside of this universe, to explore, make maps of what's inside of here, and understand better how it began and its ultimate fate. So our planet is right in the middle of this enormous sphere of space, our universe.
And the shape is spherical, or this is only a model?
So what's spherical here is simply the part of space that we can see. So this is a little bit like if you and I went for a walk in Cluj on a day with a lot of fog, then we could not see very far. Maybe we can only see 100 meters in all directions. Then it will look to us, all we can see is a sphere of radius 100 meters. In each direction, if we look 100 meters away, it just looks like white fog.
Oh, yeah.
And that does not mean that we are in the center of something. It just means that we are in the center of the sphere that we can see. If we walked somewhere else, we would see a different part of the space in Cluj of radius 100 meters. And it's the same with our universe. If there's another galaxy over here, the people who live in this galaxy, they would call this their universe, this part of space. In the case of the fog example, the reason we can't see farther away is just because there's something blocking the light. There's the fog in the air. In the case of our universe, what's blocking our view is not that there's anything in the way. It's just that it takes time for light to go from one place to another. So normally when we turn on the lights in this studio, it feels like it gets light immediately, instantly. But actually, if we measure very carefully, it takes 1 nanosecond, 1 billionth of a second for light to go this far. So if you look at the sun, for example, it's so far away, it took 8 minutes for the sunlight to get here. If the sun were to suddenly stop shining, we wouldn't notice, for 8 minutes. And if somebody were looking at us from a distant solar system, it might have taken 300 years for the light from Earth to get there. They would not see then Cristian Mureșanu and MaxTegmark discussing cosmology, but they might see maybe Vlad Tepes fighting against the Ottomans because they're seeing the way Earth was in the past. So what this means is that if you look super far away, there are places in space which exist, which are so far away that the light from there has actually not had time to reach us yet, because our universe had a beginning. Our universe is only about 14 billion years old, and if there are things that are sufficiently far away, the light has not reached us yet. And what parts of space can we see? This is the part from which the light has had time to get here so far. If you want to know what's here, you have to wait 1 billion years longer until this light also has time to reach Earth. So this is why
how big is the universe? And what are the methods used for measuring the size of our known universe?
So that's a wonderful question, because again and again and again, we humans have been surprised to realize that our universe was still bigger than we thought. Over 2,000 years ago, Eratosthenes in ancient Greece, in Alexandria, figured out the size of the Earth. And people were very impressed. Wow, it's enormous, this planet, much farther than anybody had traveled. And then, of course, later we realized that Earth was not everything. Earth was still just a small part of this much bigger solar system. And it was quite difficult to figure out, actually, the distance from the Earth to the Sun. The ancient Greeks got it wrong and thought that the solar system was about more than 10 times smaller than it actually was. So it was only actually in the last few hundred years that we realized how big our solar system was. And if you look at if you are, and yet the stars are much, much farther away than the planets that we see in the sky. So the stars, as we see at night, as I mentioned, might be so far that it's taken hundreds of years for the light to reach us. And we know that actually through a very clever technique. If you try hold your finger up in front of you like this, or maybe your pencil like this.
Yes.
Take your thumb and then blink with your left eye and your right eye like this.
Oh, yeah.
And you know what? You notice it looks like your finger jumps back and forth.
Yes.
It's
yes.
Left, right, left, right. If you put your finger closer to your eyes, and those who are watching this program should try the same thing. Look at your finger and keep blinking with the left eye, the right eye. The closer your finger is to your face, the more it jumps. So you can use this to figure out how far away the finger is. And this is actually how our brain uses the fact that we have two eyes.
And how is this method called?
So when you start talking about the eyes and how the brain figures out how we see, this is called stereoscopic vision. But we can use the same thing in astronomy. It turns out that if you, during the course of a year, if this is Earth, and the Earth is going around the sun, when you take photographs of the sky and the stars in the summer, Earth is in a very different place from in the winter. And what you see is that some stars, if you take a photo in the winter and in the summer, some stars jump back and forth.
Yes, yes.
Just
they
like the
have
finger does.
some oscillations. And
this is called parallax in astronomy, and it's this exact same idea. And the more the stars jump in position between winter and summer, the closer they are, and we can use this to measure exactly how far away they are.
Yes.
And the result is that some stars are incredibly far away. And so, when, for example, when my grandmother was a child, when she went to school, that was what they thought was the entire universe, our solar system, and then a bunch of these stars. Only in 1925 did it become clear that actually our universe is much bigger, that actually we are part of this galaxy, our Milky Way galaxy, with hundreds of billions of stars that form this beautiful pizza-shaped disk with spiral arms, which is so big it takes 100,000 years for the light to go from one side to the other. And that there are also other galaxies that are so far that it takes millions or even billions of years for the light to reach us. And in fact, I've been very lucky in my career to get to spend a lot of time on this project called the Sloan Digital Sky Survey, where we made the biggest map ever of our universe in 3 dimensions. So we mapped out inside of this sphere, where are all these galaxies in 3D, and then you can put all this information in your computer, and you can make a flight simulator program and fly around in our universe and see that we humans in our solar system are all part of something much bigger. And
but we are returning back to this idea in our next parts of the program. How can we learn about what happened billions of years ago?
Yeah, so it's quite interesting that it's easier for us to figure out what happened billions of years ago than to what happened exactly 50 years ago, or what happened during the Romanian Revolution and so on. Because, as we talked about earlier, the sky is a little bit like a time machine. When you look into the sky, you actually see the past. We see the sun 8 minutes ago, we see stars hundreds of years ago, thousands of years ago, and we can see galaxies the way they were billions of years ago. And what we've discovered, which is very interesting, is that when we look it seems like in all directions in the distant universe, things look fairly similar over there and over there. We see lots of beautiful galaxies. And that means that probably it was also quite similar here billions of years ago to how it was in all those other places. We can see how it was over there billions of years ago, far away with a telescope. We can see how it was over there billions of years ago by looking with a telescope. And we can therefore learn a lot about what it was probably also like over here. And what have we learned? Well, the way I think about it is if you imagine that that I'm teaching, I'm giving a lecture, I'm standing up and I'm looking into the classroom. And if we imagine that each of the people sitting in their chairs are galaxies, what you see is very strange. You see very old people in the front row, and then you see slightly younger people, and then you see teenagers, and then you see a row of 10-year-olds and a row of 5-year-olds, and then you see a bunch of babies sitting in the back, and then behind them there is a row with no people. And then at the very end, at the back of the room, the wall is glowing in a strange way. That's sort of what our universe looks like. What does that mean? Well, remember we're looking farther and farther back in time? So the galaxies we see nearby are old. They are as old as our own galaxy. But when we look farther away,
they are much younger as we are looking much further.
Exactly. So we are seeing that when our universe was young, of course, the galaxies then were also young. They hadn't had time to grow old. The galaxies then are smaller. They are not finished in their development. And when you look very far away, you see just tiny baby galaxies that have just been born. And I mentioned the last row has no people in it at all. That's because if you look really far away, there are no galaxies. It's just dark. Because you're looking so far back into the past that you're looking at the time before the galaxies were born. And all there was at that time were the raw materials, the gas from which the galaxies were later formed. So it's fantastic. We can see the history of our universe in front of us like this with a telescope by just looking really, really far away.
But in the same time, the things which we are looking at very, very far away, we are not sure if they still exist at this moment.
That's right, and in some cases they do not exist. We've learned that stars are a little bit like people. They are born, they live, and then they die. And we are lucky that our sun is a very long-lived star. Our sun is about 4.5 billion years old, and it will live for another few billions of years. But some stars are much bigger than our sun, and they shine much brighter, and they die much younger. Sometimes they die in a big explosion. And many of the stars we can see with telescopes are actually not there anymore. Many of those galaxies we can see with the Hubble Space Telescope, if you looked at them, if we could see them today, would look completely different.
What are the most important periods in the history of our universe?
So it's very interesting. Just like in human history, there are certain distinct periods that were quite different. We learn in school about the Roman Empire, about when the Ottomans controlled parts. We're here in Romania and the Revolution and so on. Similarly, in the universe, there are these different periods. If we start today and we go backward, right now we might call this the galaxy period. There are these galaxies with stars and planets and life. The first thing that's really striking when you look a little bit farther away is you see that all of the distant galaxies are moving away from us. And this is what we mean when we say that our universe is expanding. Everything is flying apart. Now, when we look at a picture of space, we see galaxies and we see black in between. But that black is not vacuum. It's not empty. It's actually gas, mostly hydrogen gas. It just looks black because it's transparent. And we all know that if you take gas and you make it expand, it gets colder. That's how a refrigerator works, or an air conditioner. So our universe has been getting colder and colder, which means in the past it must have been hotter. And so when we go farther and farther back in time, we have a universe which is very hot. And if we look at the way our universe was about 13.8 billion years ago, about 400,000 years after the beginning, it was so hot that the gas actually turned into a different form, into a plasma. We learn in school that if you take water, and really cold water, it's solid, it's ice. You warm it up, it turns into liquid. You warm it up again, it turns into gas, steam. If you heat it up, a gas up, it turns into a plasma. And a plasma is not transparent. So the way it looks is, if you look into the universe far away, you see transparent gas, and then eventually you see plasma. So it looks like a wall of plasma that you cannot see through behind all the galaxies. Yes. That's why what I meant when I said that at the back of the classroom, the wall, there's a glowing wall. And that is what we see pictures of here at the edge of our universe.
But this is a thermographic map, a temperature.
That's right. That's exactly right. Because this plasma...
So the hottest are the red.
Yes.
And the bluish are colder regions.
Exactly. And so this plasma was very hot. It was about 3,000 degrees, about half as hot as the sun is on this outside. And in all directions, if we look really far away, we see this wall of plasma. So it looks like we are surrounded by a wall of plasma. And fortunately, this radiation from the hot plasma cooled off when the universe expanded. So when it comes to Earth, actually it's very cold. It's only 3 degrees above absolute zero. It's microwaves. You need a microwave camera to take these pictures. And these pictures were taken by by the Wilkinson satellite from space with a microwave camera.
Oh, I heard about 3 different satellites which took some pictures, Kobe,
Yes.
the Wilkinson map, and Planck.
That's right. So for
Yes.
the first to discover that there was this radiation, the first satellite to make maps of this radiation was the Kobe satellite.
The Kobe, but it was not such a good resolution.
No, those pictures were very fuzzy.
Yes.
But it was a revolution in cosmology, the discovery, when it was made in 1992, and George Smoot and John Mather got the Nobel Prize, actually, for this wonderful project, which I think they deserved. But then this American satellite took these better pictures, and then there's a European satellite, which has made even better pictures, which I'm very excited about. I actually worked a lot on, back in 1995, on when we were writing the grant proposal to get funding from the European Space Agency for this. And I'm very happy that this past March, this satellite released these beautiful maps, which are the best maps we have so far. And you can think of these pictures as baby pictures of our universe. You can look at baby pictures of me, you know, when I was tiny. This is what our universe looked like as a baby. It was just this plasma. And you also asked a very good question, why does it look hotter in some places than others? Well, basically, there are two things which have changed about our universe since this early time. One is that the universe has expanded, which has made it transform from being very hot to being cold, from being very dense to being more rarefied. But the other is it's changed from being very simple and boring to being very complex and interesting. Because back then, there were no galaxies. There was just gas, much like the air in this room. But over time, the gas clustered and clumped into more interesting things like galaxies, stars, and planets, and people. And for that to be possible, there must have been some tiny differences from place to place already in the beginning. And that's what you can see pictures of here. It's, when we talk, can you hear me now?
Yes.
That's because of sound waves. So if you take a microphone and you measure the pressure of the air right here, sometimes it's a little bit higher, sometimes it's a bit lower because I
Yes.
speak. It's about 1/1000% higher in some places than others, which coincidentally is exactly how the gas in our early universe was. 1/1000% more gas in some places and less in others. And then gravity transformed this gas with some sound waves into everything interesting we see. Because if the gas were completely uniform, then it would stay completely uniform forever. But if you have a little bit more gas here, then the gravity from this will pull more gas into this. The gas will fall down towards here, and then you have a bigger clump with more gravity, which can take more gas and more gas. It's unstable, and eventually you make stars and galaxies.
Precisely how old is our universe?
So this is very interesting because we used to argue about whether our universe was 10 billion years old or 20 billion years old when I was a graduate student. Now we argue about...
When I was very young, I heard 20 billion years old.
Yeah, but that's right. But then some people said, no, it's only 10 billion years old, and they could never agree. So cosmology got a bad reputation for being very inexact. People could not make good measurements. Now, after the Planck satellite, we argue about whether it's 13.7 billion years old or 13.8 billion years old. So, and it's probably 13.8 now. So we're getting great precision. So how do we do this? Well, the basic idea is actually quite simple. If there has been a bank robbery in Cluj, and the police on the highway, they stop a car with the robbers in a car full of money, and the car is 100 kilometers away from the bank, and the car was going 100 kilometers an hour, they can figure out when the bank robbery happened. It must have happened 1 hour ago. You just take the distance and you divide it by the speed of the car. And we can do the same with our universe. If we see a galaxy that's very far away, we can measure its distance, and we can measure how fast it's going away. So we can figure out how long ago was the galaxy here, just like we can figure out how long ago were the bank robbers at the bank.
Yes, but there are something very interesting. The car can go away from the bank, depending on what the burglars see the danger. as constant speed, or it can accelerate, not to being caught.
Exactly, and I'm very happy that you asked this, because this is exactly a complication that we have. If you ignore that possible complication, then you only get an approximate answer. You say, well, it's approximately maybe 13 billion years, 14, 15.
It is expanding, but how it is expanding?
Exactly. But to get an exact answer, you really have to know, are they accelerating or are they decelerating? And as a matter of fact, we've been able to measure that now. And it turns out, interestingly, we'll come back and talk about this later, our universe started out by for the first half of the age of our universe, the universe mostly decelerated. That's what we expect, because if I take this pencil and I throw it up into the air, eventually it will stop going up. Gravity decelerates.
Yes, yes.
So the galaxies flying apart will be decelerated. But strangely, during the second 7 billion years, our universe has been accelerating again. And we'll come back and talk about why. But when we put this into our calculations, it turns out that the acceleration and the deceleration almost cancel each other out, and we get back almost exactly the same answer as if we just do the simple calculation that we talked about first. And we get 13.8 billion years. That 13.8 billion years ago, almost everything was in the same place, and our universe was super hot and super dense.
Let's go now towards the very beginnings, and please tell us what is the most plausible theory of how the universe started.
So I should tell you first that we don't know, is the honest answer. There has always in the history of humanity been a frontier of our knowledge. We always knew what happened yesterday, but there was always a time in the past before which we didn't know. And gradually we have been able to push this frontier of our knowledge back in time. As I said, we can see what happened all the way back to 400,000 years after the beginning. And so we understand that very well. We actually have also been able to push the frontier back to the first second after the beginning. Just like we know that there are dinosaurs, because even though we can't see them, because we found fossils, we found bones of a Tyrannosaurus rex in the ground and so on, we have also found fossil evidence of what happened earlier during the epochs we cannot see. So we know that our universe was hotter and hotter in the past. If you take hydrogen gas, and you keep making it more and more hot, then eventually it will become as hot as the center of the sun, many, many millions of degrees. And we know from physics what happens when you make hydrogen this hot. The same thing is happening inside of the sun right now. You get nuclear reactions, fusion reactions, where hydrogen turns into helium and produces lots of heat. So you predict that our entire universe, when it was about 1 second old, was a giant fusion reactor which took the hydrogen and made helium. And but the fusion reactor turned off because the universe expanded and got too cold. And when you calculate how much helium did it have time to make, the answer you get is about 1/4, about 25%. But we can look with our telescopes and we can measure how many percent of the universe is helium out there and far away, and we get 25%. It's very, very impressive. And we can also calculate how much lithium and deuterium and helium-3 we get, and it agrees very, very well with what you predict from this cosmic fusion reactor. So we're actually quite confident that we understand what happened after the first 1 second or so. Before that, it becomes much more speculative, and we honestly don't know, but there are a lot of interesting theories. And the most popular theory in the cosmology community for what happened before that is called inflation.
Oh, yes, yes. This one I heard about. Yes, the inflation theory, but it began somewhere in 1980s. Alan Guth formulated.
Yeah, my MIT colleague Alan Guth.
Your colleague with Alan Guth?
Yes, he's in my department. He's a very nice guy. Very nice guy.
And how did you cooperate with him? And
we're good friends. He was over for dinner at our house a few weeks ago. He's a very nice man, and we've also written papers together on other things more recently. But
so you work together with him, yes?
Yeah, and we have students together. I feel very lucky to get to work at MIT together with such wonderful people. So Alan Guth had this very radical idea where you have to make one very strange assumption. You have to assume that there is a kind of stuff which does not dilute when you expand it. And what I mean by that is if you take, for example, if you take ordinary stuff like air and you expand it to twice the volume, the density gets lower because the total number of atoms is the same. The total number of kilograms must stay the same. But he said, suppose there is another kind of matter which will not dilute much. So I take 1 kilo, I expand it, now I have 2 kilos because the density stays the same. That sounds very strange, but if you assume that, then you can calculate using Einstein's equations that, in fact, what it will keep doing is it will keep doubling its size, doubling and doubling and doubling and doubling and doubling. And if you keep doubling a number over and over, very quickly you get something enormous. You get 1, 2, 4, 8, 16, 32, and soon it gets very big. And in fact, this stuff in the inflation theory, it kept doubling its size extremely fast. So after a tiny, tiny fraction of a second, it had already created something which had more mass than our entire universe in it, and it was flying apart very, very fast. So what's interesting about this is if you start with a tiny amount of this stuff, much smaller than a single atom, it can explain what put the bang into our Big Bang, why there was this explosion, and why you got all this stuff. And after he developed this theory, and other people like Andre Linde and many, many other scientists elaborated on this, it became clear that this theory actually explained a lot of mysteries that we didn't understand, properties of our universe. And it also gave a beautiful explanation for why there are actually these patterns, why it's a little bit hotter in some places in the early universe than others. And the Planck satellite that just gave us these new measurements has beautifully confirmed this inflation theory. So even if it sounds like a very surprising assumption that there is a strange kind of substance, that it's predicted all of these different things which agree very well with what we measure, and it seems to really work. And that's why people take it so seriously. And there are more things that it's predicted that we're also hoping to test soon. So this is the best theory we have so far for what happened very, very early on.
Yes, but you know, this is such a fascinating subject. We are fascinated by everything which is unknown. So my next question would be, do we know what happened before our Big Bang?
So,
or rather, if we can speculate something about.
So the answer to your first question, do we know, is no. But can we speculate? Da, absolutely. There are many, many different speculations about what happened before our Big Bang, and even some of the speculations are even more radical, saying maybe it doesn't make sense to talk about before. For example, if you ask, what is there north of the North Pole? What would you say? It doesn't really make sense.
Yes, yes.
And Einstein actually taught us that the whole idea of time that we think we understand so well is actually is much more subtle than we thought. And it might very well be that our Big Bang was the beginning, not just the beginning of our space and all this stuff. Maybe it was in some way the beginning of time also. Or maybe all there was some strange quantum fuzz. We will talk more about this in the next program, about quantum mechanics.
Yes, yes.
Where it somehow didn't really make sense to talk about space or time. And then gradually, time and space sort of emerged. There are many, many different speculations. I feel that right now, the frontier of our knowledge is basically to try to test inflation. And if we can make a lot of progress on that, we'll be in a better position to try to take the next step.
And among the speculation, is there anything about the possibility that maybe time and space to be much older than the universe?
One category of speculations is that there was something before our Big Bang, that maybe there was our universe collapsed and somehow bounced back again. There are a lot of problems with that, so most people don't believe that that works, that you would just make a giant black hole instead and nothing could come out. But there are some people who are pursuing that, and I think actually it's really fascinating that, as you said, we humans, you know, it's hard for us to understand things much bigger than us. It's really remarkable that we've been able to understand as much as we have, because, and this is something that I think we should be very grateful for. We are much smaller than the stars.
Yes.
But somehow the properties we have to be able to think critically and be creative and use our imagination has enabled us to really figure out remarkable
within
things.
the scale of the smallest, tiniest possible particle and the largest cosmic object, we are in the middle. Someone took a
Yes.
map, you know. And,
That's right. That's right. And not only that, but we're also the most, your brain is also, our brains are the most complicated objects that we know of in our entire universe. We are much smaller than the sun, but much more complicated and complex, and I think in that way much more interesting. And we are able to think because we're much bigger than the atoms, and because we're much smaller than what we're part of.
Yes, and also there is a theory that space and time would not be only some concept, some abstract concept, but space, for example, would have a geometry which is creating, expanding from a tetrahedron shape, which is the smallest possible three-dimension space which we can create. It's a tetrahedron. We cannot create something which is less point, but the largest one is the sphere, which has an infinite number of points.
Yeah, there are many interesting theories like this.
Buckminster Fuller, for example.
Yes, exactly. And there are many interesting theories like this, and I think it's important that we are humble and modest, and that we never dismiss theories and say, that must be wrong because because it seems counterintuitive or strange. Our job as scientists is not to tell our universe how to behave, to conform with our preconceptions, but to be modest and to look at our universe very carefully and see how it actually is. And maybe it is indeed in some way which is very different from how we thought.
So we should be open to all possibilities, because it will never know maybe in the future which one will be more accurate than the other.
Absolutely. I'm glad you mentioned this, because to me that is the single most important idea in science. We should be open to all possibilities. We should always question, we should always ask questions, we should always question authority. Everything we believe in now, it might still be wrong. Sometimes even Newton's theory of gravity, for example, which was very successful, it was not quite correct, and Einstein came up with a better theory, and so we should always be open for new possibilities. If we're not open to new possibilities, then we will miss the opportunity to make wonderful discoveries and also to discover new technologies.
Yes. I also read a lot about a theory which, due to the copyright problems, I am not allowed to present to our viewers, and I made an interview with that physicist, but later on his manager forbidden me to present it. And I am happy you are now here, and you can either confirm or deny, or we can talk freely about all the theories of the universe. What is happening with the universe now? Is the universe expanding, contracting, or dissipating, accelerating or decelerating?
Yeah, so right now, we know for sure that our universe is expanding. So again, what we mean by that is if you take any two galaxies far away from each other, they are going still farther apart. But the second question is, how is that expansion changing? Is it expanding faster, accelerating, or is it decelerating? And as we discussed, the natural guess would be that things should decelerate, because gravity always tries to slow down something which is going up. But interestingly, we've measured now very carefully with two different methods that our universe is now accelerating. And this is so shocking that it was hailed as the breakthrough of the year about 13 years ago, and it was given the Nobel Prize in physics, this discovery. And the reason that it is accelerating is that there is something which is creating an anti-gravitational force. So again, normal gravity, if you throw something up, will make the thing gradually move up slower and slower until it stops. So if something is falling upward faster and faster, there must be something which is instead pushing instead of pulling.
Yes.
And that's something, we don't know what it is, but we've made up a name for it. We call it dark energy. And incredibly, it makes up about it makes up about 70% of all the stuff in our universe. Most of the stuff out there is actually not atoms, the kind of material that you and I are made of, and not even dark matter either, which we can talk more about. But it's this strange dark energy. And we don't know what it is, but we really want to know what it is, because this dark energy is what's going to determine ultimately the future of our universe. And another interesting thing about dark energy is it's made people believe more seriously in inflation that we just talked about. Because before you could say, well, yeah, it's a nice theory, it predicts nice things, but surely there cannot be a substance which has this property that it won't dilute, that you take 1 kilogram and it expands into 2 kilograms. That's ridiculous. But dark energy is exactly like that. And we know dark energy exists. That's what the Nobel Prize was for. So if this kind of stuff can exist now, it's actually not so crazy to think that it could have existed also in our early universe and caused the inflation.
But is that somehow part of someone calculated the density of the vacuum and obtain such a huge density that it is almost unbelievable? The entire mass of the normal matter of the universe is, if we could contract it, it will be comprised into a centimeter cube of...
Yeah, so it's very mysterious what this stuff is, and if you make the simplest calculation you can as to what should the density of dark energy be, or the density of M, I should say that dark energy is not like water or salt or some ordinary substance that you can have, because I have water here, but there's no water there. You can have a clump of ordinary matter, but dark energy is not like that. Dark energy has the same density everywhere in space. It's completely uniform. So it's as if it's a property of space itself, that the empty vacuum has a density. And when you make the simplest possible calculations of how dense the vacuum should be, you get crazy big numbers.
Yeah.
So for a long time people said, those calculations have to be wrong. The true answer is probably 0. But now we've measured it, and the answer is not 0. In fact, 3/4, or 70% of the stuff is dark energy. In the next program, when we talk about parallel universes, I'll tell you more about an explanation on how
Yes.
how that might work.
Yes,
but we should also mention, I think, dark matter, because I said we humans have to be humble, and we have become a little bit more humble when we realize that not only is our universe much bigger than Earth, but we are not even made of the majority substance. We are made of atoms. Everything we see is made out of the same kind of particles. But we are only 5%. 70% is dark energy, so that means 25% are still missing. What's that, 25%? That's what we call dark matter. And if you look into space, sometimes you can see things, you can figure out that something is there.
Let me a little refresh. From 100%, 70% is dark energy.
Yes.
20% is dark matter and 5% is the normal matter we see?
Yeah, let's say about 25% dark matter and about 5% is normal matter. Yeah, all the atoms, gold, hydrogen, oxygen, iron, all that stuff, only 5%.
5%.
So there's 5 times more, 25% of this dark matter. What is that? Why do we believe that it exists? Well, if you look at for example, the sun, and you see that Earth is going around the sun, you can figure out how heavy the sun is, because we know that the reason Earth is not going in a straight line but in a circle is because the sun is pulling on Earth. So that gives us a way of figuring out how many kilograms are in the sun. And similarly, you can figure out how many kilograms are in the Milky Way galaxy. Vera Rubin in the 1960s, she decided to weigh our galaxy by looking at stars that were orbiting around our Milky Way. She looked at how fast they were going and at what radius. And she realized that actually the Milky Way weighs much more than the stars in the Milky Way. So there's more stuff in our galaxy which we actually cannot see. It's not stars, it's not gas. What is it? And now we've convinced ourselves that this other stuff is not made of atoms at all. We call it dark matter. And we don't know what that is either. It's another big mystery.
Yes,
but most people think that the dark matter is maybe some kind of new particle that we haven't been able to detect yet in our laboratories. But there are particles that are very shy. For example, there's a kind of particle called the neutrino, which we have detected now. They're so shy that if a neutrino comes and it hits my hand, it goes right through and out on the other side. Then it hits the ground and it goes through Earth and comes out maybe in China and continues into space. And once in a while, if you build a really big detector and you're very patient, sometimes you can catch a neutrino. And the neutrino's also got a Nobel Prize now for being discovered. So we think that the dark matter is probably some other kind of particle like that that's just very shy. It doesn't like to interact so much with atoms, but once in a while it does. And there are many experiments now around the world trying to catch dark matter particles. And another very exciting development is in Geneva at CERN, at the Large Hadron Collider. Many scientists, including many great Romanian scientists, are working on the Large Hadron Collider.
Oh, yes, yes.
This machine which collides particles near the speed of light and smashes them together to see what comes out.
And the institute is right here nearby the studio. They have a contract with CERN in Geneva, and I interviewed the specialist over there. It's very nice.
And I saw them when I came in here also, and what they're doing is it's possible. It might be possible at CERN to actually produce dark matter, because it might be that in some of these collisions, dark matter particles might come flying out, and that would also be a sensation, because then we would, which would certainly give the Nobel Prize, if we discover the particle that makes, or particles that make up the missing 25%. So this is one of the biggest challenges right now in physics, to try to figure out what is the dark matter. Some people try to catch it, some people try to produce it.
But regarding this expanding the universe, if it is accelerating, there are more possibilities. It will be dissipating, or it will continue to create more and more galaxies and stars?
Yeah, that's right. So all we know is, first of all, we know that right now our universe is accelerating. But what about our future? We all want to know about our future, what's going to happen. And there are several different possibilities. And what will ultimately happen really depends on the dark energy. Because right now, 75% of the stuff is dark energy, and the dark energy is not diluting. But all the other stuff is diluting, so eventually there will be 80% dark energy, and 90% dark energy, 99% dark energy. So what the dark energy does will determine our fate. So what are the possibilities? One possibility is what we call the big chill, that our universe just keeps expanding forever, getting bigger and bigger and colder and colder. Another possibility is that somehow the dark energy starts to dilute and eventually goes negative and just causing deceleration, and that our expansion could stop and our universe would come crashing back together again in what we call the big crunch, basically making a giant black hole out of everything. And a third possibility is that the dark energy instead goes really crazy and starts accelerating things faster and faster and faster, creating what we call the big rip, when the expansion becomes so fast that just everything gets torn apart a finite time into the future. And then yet another possibility, you see, cosmologists have a lot of imagination for coming up with bad things that can happen, is that that you could have what we could death bubbles.
Yes.
That maybe somehow space itself is unstable somehow. Like if you, for example, if you take water and you leave it in a bottle of water, you leave it in your car in Cluj in the winter when it's freezing, if you don't touch the water, it can become super cooled. It can stay liquid even though it's below zero. But then when you touch it, all of a sudden, poof, it all freezes all at once. Some people think maybe our space is like that, our space could somehow freeze into a different kind of space.
So it can have weird properties just like water,
maybe.
Which some scientists also discovered that if the water is cooled suddenly at minus 80, 100 below zero, it creates something totally different.
And if this were to happen, if this is possible and were to happen in our space, then you would get like a bubble of destruction.
Yes,
because the space would start changing.
We have time only for one question in this program. I should just say,
people shouldn't worry so much about this. I don't want to scare our viewers too much. The most likely scenario is probably that our universe is just going to keep expanding for a very, very long time.
Yes.
So we should worry more about the stupid things we humans sometimes do to our planet.
The final question for this part. What does studying the universe tell us about life and our significance in this vast space and time?
That's a wonderful question, and I have to confess to you that I have changed my mind about this, because the more I learned about our universe, the more I learned about how big our universe was, the smaller I felt and the more insignificant I felt. But then something happened which completely changed my perspective. We live in a universe which is very, very large. So far, we have never found life on any other planets, and this is also a very exciting topic. You can make it. You probably have other programs about, but it's actually it is a possibility that we are alone in our universe. That there is no. It might be possible that there is no other life in here, anywhere in our universe, as advanced as us, able to build telescopes, for example. So let's imagine, just for a moment, if that is true, what does that mean about how we should feel? It means that we should feel very significant. If we look at the galaxies with our telescopes and we say, wow, this spiral galaxy is so beautiful. Why is it beautiful? Because we see the galaxy. In this sense, it's not that our universe is giving meaning to us, but we are giving meaning to our universe.
And if we would not be alone?
If we would not be alone, well, then there are very embarrassing questions we have to answer, like why haven't we seen any life yet, and why haven't they already colonized us? We know that there are planets in our galaxy which are billions of years older than Earth, and we also know that it's, according to physics, not that it's certainly possible for life to travel between planets and colonize. So we don't know whether we're alone or not, but I think it is possible that we are alone, which means that, in a way, the fact that here on this planet, atoms, we have become aware of ourselves and gotten consciousness and built telescopes and started to appreciate the beauty of our universe. In this case, that's maybe the most significant thing which has ever happened in the entire history of our universe. So we might be small, but very significant. And if you look to the future, right, then space travel is certainly possible. And if we humans don't mess up, it's quite possible that in the distant future, life will spread from this planet, and our whole universe will one day be teeming with life, right? And it would all have started then on Earth. I think we have to be very careful with humans, because I think this time that we live in is very unstable. I think we cannot just keep messing around with nuclear weapons and all the other technology we have like this for hundreds of years without either something very bad happening, which might even end life here, or us really getting our act together and creating a more stable and harmonious society. And when will this all be decided? Maybe in our lifetime. So I think that not only should we not feel insignificant, but what we and what our viewers here and what the young children in Romania who can go out and study science and so on and change and affect the world, what they do in their lifetime is probably the most significant thing to ever happen anywhere in space and any time in the history of our universe.
Thank you very much, and I hope to meet you again next time for part 2.
Ne vom întâlni data viitoare la partea 2.
Okay, great. Aceasta a fost prima parte a discuției noastre despre cosmologie și vă încurajez în mod deosebit și cu insistență să vizionați partea a doua data viitoare la aceeași oră, deoarece vom vorbi despre lumi paralele, mai degrabă universuri paralele, și este pentru prima dată când abordăm un astfel de subiect care poate până nu de mult la noi în sală era considerat fie de sorginte ezoterică, fie pseudoștiință. Noi vom face o abordare științifică, cu toate criteriile respectate, așa după cum sper că vi le reamintiți la discuțiile noastre cu domnul profesor Daniel David. Înainte de a încheia, doresc să vă anunț faptul că domnul profesor MaxTegmark vă stă la dispoziție pe pagina sa de Facebook cu orice întrebări legate de cosmologie și chestiuni discutate în cadrul emisiunii. Fiți alături de noi data viitoare la o nouă întâlnire cu știință și cunoaștere. Bun găsit la emisiunea Știință și Cunoaștere. De multe ori sunt abordat pe internet de persoane care au o credință uneori intuitivă, alteori obsesivă în existența lumilor paralele. Fiind de formație inginer ca și pregătire, eu nu pot crede în lucruri lipsite de o logică minimală sau o demonstrație. Dar dacă această demonstrație nu e posibilă, atunci poate că există o altă modalitate de a le înțelege fără să rămân la nivelul unei credințe oarbe. Astăzi vom vorbi despre lumile paralele și veți afla faptul că există o nouă formă de înțelegere a acestui concept care nu se bazează pe misticism, ezoterism și percepții extrasenzoriale la care prea puțin dintre noi ar avea acces. Sunt întru totul de acord că anumite forme de cunoaștere nu pot rămâne la nivelul unor teorii și că în cele din urmă ele ar necesita un experiment direct. Însă, din propria mea experiență de viață din ultimii 24 de ani, am aflat un lucru foarte important. Nu se poate aborda corect și cu rezultate rapide cunoașterea ei în forma ultimă și experiențială dacă se sare peste etapa înțelegerii raționale corecte. Am încercat aceasta și nu am reușit. M-am ghidat deseori după o cunoaștere confuză și incompletă, oferită de misticism și ezoterism, dar fără să pot ajunge la rezultatele practice și fără să pot avea acea înțelegere cu adevărat completă. Am citit sute de cărți despre vindecare, dar nu am putut aplica cele citite pentru a-mi regăsi sănătatea. Am citit sute de cărți despre înțelegerea lumii și a universului, dar nu am reușit să obțin nici măcar o claritate la nivelul rațiunii asupra tuturor acestor nedumeriri metafizice și întrebări existențiale care ne bântuie pe mulți dintre noi. Dar am rămas cu setea de cunoaștere și cu imboldul de a merge înainte și de a mă ridica după fiecare căzătură, până când am început să dobândesc acea cunoaștere experiențială la nivelul deocamdată a unor mecanisme biologice. Dar acest lucru mi-a întărnit și mai mult încrederea în știința clasică și în metodologia științifică. Și astfel am revenit treptat la aceste abordări, constatând cu uimire, dar și cu bucurie, faptul că știința de azi a făcut progrese uimitoare, care nici măcar nu erau credibile sau imaginabile în urmă cu 24 de ani. Vom vorbi despre toate acestea în minutele care urmează cu invitatul emisiunii, cercetătorul MaxTegmark, cosmolog de origine suedez-americană, profesor la Institutul de Tehnologie din Massachusetts, Statele Unite. Pe măsură ce am realizat munca laborioasă și pretențioasă a traducerii și subtitrării celor aproape 3 ore de interviu, viziunea mea asupra vieții și universului a început să cunoască schimbări fascinante. Am aflat răspunsuri pe care nu le-am găsit nicăieri în altă parte, sau mi-ar fi fost imposibil de înțeles la nivelul științei fundamentale. Hello and welcome for the part 2 of our program regarding cosmology, and I am so happy you are back again in our studio in Cluj.
Mulțumesc foarte mult.
We are now continuing our fascinating discussion with the parallel universes, and obviously the first question is what are parallel universes and how many kinds of parallel universes are there?
It's a very good question. So before we talk about parallel universes, let's remind ourselves just a little bit about what we mean by our universe. As we talked about in the last program, this is our universe, the three-dimensional sphere, the spherical part of space that we can see, that light has had time to reach us from during the 13.8 billion years since our Big Bang.
Yeah.
So that naturally begs the question of, is the part that we can see everything that exists, or is there more? And if there is more, then we call that parallel universes. And to me, the most interesting question actually is not whether parallel universes exist, but how many different kinds of parallel universes there are. And we can talk about them one by one in detail later, but just to give an overview, I think there are 4 kinds. First of all, space itself almost certainly does not end here at the edge of what we can see. There's more space, maybe an infinite amount of space that goes on in all directions, which means that if there's a galaxy over here, the people who live in this galaxy will say that this is their universe. You have all these level 1 parallel universes, as I like to call them, which are much like our own, but just places very, very far away in space. Then there's a second kind. In fact, in my new book here, Our Mathematical Universe, I talk about all of these 4 kinds in great detail. The second kind of parallel universes are even farther away. They're, in a sense, they're so far away that you could never get there even if you traveled at the speed of light forever, because space between us and them are still undergoing this inflation process that we discussed, so that it's sort of like if you try to walk down the up escalator and you're walking slower than the escalator is going, you never get there. And those universes are in a way more interesting than the first kind, as we can come back and talk more about. Then there's a third kind of parallel universe, which I think is in a sense right here, which has to do with quantum physics. When we study the very, very small, we discover that everything is made of particles which can be in several places at once. And it seems as if in some way our lives also can branch out in many different ways in parallel. And finally, there's a fourth kind, the level 4 multiverse, which is the largest and most diverse set of parallel universes, which is the main focus of my book, where even the fundamental equations of physics can be different. And we can come back and talk about each of these 4.
Oh, that is very fascinating, yes. So let's start with level 1. Tell us a little bit more about level 1 parallel universes. Where can we find them?
Yeah, actually, even before we talk about level 1, we should probably also say a few words about whether this is actually science or whether it's really just science fiction or philosophy, because it sounds kind of crazy, doesn't it?
It's like Star Trek science.
Exactly. So it's important to remember that parallel universes are actually not a theory, but they are predictions from certain theories. So, for example, black holes and what happens inside of a black hole is a prediction from a theory, from Einstein's theory of gravity, general relativity. So if we ask, is this science or science fiction? It depends on whether we think of Einstein's theory of gravity as a scientific theory or not. And the definition of a scientific theory is that you can test it, that you have an opportunity, that there's some experiments you can make or measurements which have the possibility of ruling out the theory and showing that it's wrong. And why do we believe in black holes? Well, we can actually never go into a black hole, see what happens, and come back and tell our friends because we can't get out. But we still take this seriously. Why? Because Einstein's theory of gravity also predicts lots of other things that we can test. Einstein's theory of gravity predicts that Mercury will orbit around the sun in a funny sort of way, which we've measured, and it works. It predicts that light is bent by gravity, which we've measured, and it works. And because Einstein's theory has passed all these other tests, we've tested so many of its other predictions, we also then take seriously its predictions for things that we cannot see, like what happens inside black holes. And it's very analogous for all the kinds of parallel universes that we will be talking about, that there is some theory which predicts a lot of other things, and it also predicts these parallel universes. So that's why I feel it's perfectly okay for us scientists to talk about this as in the context of science, not just in the context of science fiction. So you asked me about the first kind of parallel universes. Where can we find them? So basically, parallel universes are universes just like ours, just farther away in space. So they're still in this thing.
Just like for our viewers to understand, we have more balls like these in such a large space that even any other contact is totally impossible.
That's right. So let's assume for a moment the simplest kind of space that just goes on forever, like we all imagine as children. It's hard to imagine that space would just end. We can't see an infinite space. We can only see part of the space because light hasn't had time to reach us yet. So that means that there are all these other regions that are just as large as the region we can see, which have stars and galaxies and so on, and they are the different level 1 parallel universes.
Yes. So what make it plausible that they exist?
So the reason that the main reason we think they exist is we actually have some pretty good reasons to believe that space is much bigger than what we can see, because basically this theory of inflation that we talked about in the last program, it creates a space which is not just big, but huge, and probably infinite, and probably even infinitely big. And since we know we can only see a finite part of the space, that means that there's more that we can't see.
And it is even possible that the space itself to expand more rapidly than the universe in it.
Yeah, so then there will be parts of space exactly that we have no contact with. And so we can ask, what are these other universes like? And the level 1 parallel universes, they're very much like our universe. They have the same, if you would learn the same things in physics class, they would have gravity and light and so on. But you would learn different things in history class, because the way history happened in our universe depends on how everything started out, where the atoms were long, long ago. If the atoms had started out in a different place, our Earth would not have formed. Maybe the planets would have been in a different arrangement. Maybe our solar system would have not 8 planets, but only 5 planets. Maybe some other planet would have collided with us last week, and we wouldn't have this program. And also detailed things which happen in everyday life on our planet depend in a sensitive way on how things began.
So they could be quasi-identical, not totally identical, but have some similarities and differences.
Yes, so for example, if some atoms billions of years ago would have been in different places, then maybe Vlad Tepes's mother and Vlad Tepes's father would never have met, and there wouldn't have been a Vlad Tepes. and maybe we would all be speaking Turkish today. You know, so in the level 1 multiverse, there probably is a parallel universe where Romania is part of the Ottoman Empire, for example. And all of these things we can imagine, which don't sound physically impossible, you know, would actually then get realized. And you might think, well, that sounds very crazy, but we have to remember that if you roll the dice many times, eventually everything that can happen sort of will happen. And if you have infinitely, we know that it's not impossible to form a solar system and with a planet and evolve life, because it happened here. So if you roll the dice many times in other parallel universes, you know it's going to happen again, eventually, somewhere. You can even calculate how far away you have to go to find the nearest universe which has life and so on. And the nearest universe that has life in it then will be, things will be a little bit different from here, but eventually there will even be a universe which is identical to ours, where everything is the same. To go to one of those, you have to go very far away. You have to go about a googolplex meters, where a googolplex is one with a Google zeros after it, and one Google is one with 100 zeros after it. So it's this very long distance. But if this is true, then for the people who live there, they feel that that is real. And
yes.
they will argue about whether you and I are science fiction.
Maybe in order to jump from one universe into another would need a subspace, something like where is a shortage in the normal space, and so we are using the subspace.
Yeah, there has been a lot of discussion both among science fiction authors and also among physicists about wormholes through space-time, which could be this kind of shortcut.
Yeah.
We don't currently have the technology to build them, and it's not obvious that it's possible, but if you can do it, it would look a little bit like two black holes that are connected together, and you jump into this one and you come out of that one. And that would be by far the most efficient means of intergalactic transportation, because you arrive at the destination almost at the same instant that you start your trip.
I remember an Italian guy, but I don't know his name, I forgot it, but his theory was about subspace communication, but it's only a theory, very fictional on the present moment, but maybe interesting, just like talking about. He said that based on the Copenhagen theory, where if one pair of particles are split in very large distances, if one particle spin is modified, then the other particle pair of that one is also modifying simultaneously, no matter how much is the distance between them. So he said this could be a model how to communicate at very large distances instantly.
Yeah, this quantum teleportation, as it's called, is a fascinating technology which we can talk more about when we talk about the level 3 parallel universes and quantum mechanics. It seems as if it's actually not possible to use this to send information in the normal way, faster than the speed of light. But this is already used by companies to send information secretly in a way that cannot be intercepted by anybody, so it's a fascinating idea. I actually think, personally, I'm actually hoping that we might think it's a bad thing if we cannot travel super far away very quickly. But it can also be a good thing, because it can protect us from aliens. You know, just like it was very lucky for the Native Americans, the Indians in North America, that there was an ocean between them and Europe. So that protected them for a long time from us Europeans coming there and killing them. The fact, if it turns out to be impossible by the laws of physics for other civilizations very far away to come here, that protects us, right? If it turns out that you can make wormholes through space-time and come here from parallel universes, then we should not feel very safe, because there could be other civilizations with much higher technology which would come here
and find nothing, because this is nothing interesting to be useful for them. If they are so advanced.
So we should be humble and realize we don't know yet what's a good thing and a bad thing for us.
Maybe
we're lucky.
We should be afraid of someone which are approximately like us, but they are not. This means they are in the same situation, cannot communicate and cannot travel. But I don't think someone would ever be wanted to live on a planet while can create artificial planets and way of living, not using natural rock in space.
I hope you're right, but I think it's good that we should be cautious and careful with these things, and be modest and realize it's very hard for us to guess, what other life forms would be like, and
yes.
Our imagination sometimes isn't good enough to.
So let's talk more about level 2 of parallel universes.
Yeah, so those parallel universes are actually more diverse and interesting. It's become clear that some of the things which we learned in school as laws of physics are actually not laws that cannot be completely changed. So for example, suppose for a moment that I'm a fish, okay? And I've lived my entire life in the ocean, in the Black Sea, swimming around outside of Constanza. Yeah. And all I know is water. And so I don't even realize that there is a substance called water. I think of the water as just empty space. But if I'm a very smart fish, I could study the properties of water and say, it's made of hydrogen and oxygen, and I could write down some equations, and I could realize actually the water can come in 3 different forms. It can be liquid, like my water, and it can be solid ice, and it can be gas, it can be steam. Maybe if I'm a very ambitious fish, I could even figure out a way of swimming to near the North Pole and see an iceberg and see that there is ice. But we physicists have good reasons to believe now that maybe our space itself is actually like this. You might think this fish is stupid and we should laugh at this. But actually, maybe the last laugh is on us, because maybe our space can also freeze and evaporate. In fact, string theory, which is one of the most popular theories for understanding the building blocks of matter, suggests that maybe our space can be not only in 3 different states, but it may be in one with 500 zeros different states, lots of different states. And now the interesting thing is that this theory of inflation, which we talked about in the last program, which we think made our Big Bang and our universe, it is very violent. And it can make, if it makes space, it will actually make space in all the different states. It'll make a big universe full of space only in this state that we have, and then it will also make other universes with space in all other possible states that space can be in. And so for the fish example, there would be a whole universe with just liquid water, another universe with ice, another universe with just steam. We look around with our telescopes and we see that everywhere we can see it looks just the same. So then we make the mistake of thinking that must mean that everywhere is just the same. But no, far outside of our universe there could be a border where space changes to another kind of space. And what would these other kinds of space be like? Well, for example, there might be a kind of space where you cannot have atoms the way we have. In our space, we know that the atoms are all made out of neutrons and protons and electrons, 3 kinds of particles that are put together. But there could be another kind of space where you instead have different kind of particles. Or maybe where the law of gravity works differently, or the laws of electricity and magnetism work differently. So if string theory is correct, and if inflation theory is correct, then actually we have a very diverse and more interesting universe or multiverse on the very large scale, because there will be places in the level 1 parallel universes where we discussed the children in school there learn the same thing in their physics class and just different things in history class. But in the level 2 multiverse, they would also learn different things in physics class. They would learn, instead of learning that there are these atoms made out of 3 kind of particles, maybe they would learn that there are atoms that are made out of 5 kind of particles. Maybe they would learn that the electricity and magnetism works differently.
For example, some kind of equation would not have, for example, the force at square 2, but maybe at square 3, at cube or something.
Exactly.
Or,
instead of saying maybe x squared, it would say x cubed. Because if string theory is correct, then string theory would still be the correct, true theory that describes all of the level 2 parallel universes. But you would have different kinds of, many different solutions to these equations. Just like you can have, the equations for water can have 3 solutions: ice, liquid water, and steam. The equations of space can have many different solutions. And many of the things that we used to think were basic properties of nature are actually just telling us which particular solution we have. It's a little bit like if you ask about our solar system with our planets, it has the property 8. There are 8 planets, right? Mercury, Venus, Earth, Mars, and so on. But this number 8 is not the basic property of reality. It does not go into the basic equations of reality. It just tells us part of our address, where we live. If you explain to somebody from another galaxy where we live, you say, well, you know, we live in that solar system over there with 8 planets, not in that solar system here with 5 planets. So the 8 tells us about where we are, not about the properties of nature. And in the same way, if you explain to somebody which level 2 multiverse we live in, you would say, well, we live in that particular, this place over there where space has 3 dimensions, where atoms are made out of 3 kind of particles.
Well, you remember me about the Stargate and dialing sequence, you
yes,
know, on
yes.
the Stargate, and to use that symbols, and for getting into another galaxy, it was needed a 7th symbol, because it's not sufficient to have the 6th symbol indicating into a cube where it's the origin point, and you know, stuff like this.
That's right. So we've discovered more and more of the properties of nature that we thought were really fundamental. They were. Where I work at MIT, many of the students like to wear T-shirts that have equations written on them. They're very geeky, and for example, people like to wear the T-shirt with Maxwell's equations, which explain light and electricity and magnetism. And we like to think that these equations, we used to think that these equations that we discover are truths about the way reality works, that they can't be different. But we've learned now that many of these things in the equations are no more fundamental maybe than the number 8 about our solar system, the number of planets. But there could be other regions really far away in space where the properties of space are different, so you have a different sort of description. That's right. You can also write down the equation for how sound waves move through water and ask how fast does the sound go through water. Well, it depends. If it's ice, sound goes at a different speed than if it's liquid.
Yes, yes. But I also hear that maybe not a long time ago, the string theory had been abandoned, or not?
It's certainly not been abandoned. No, there's been a long controversy, of course, about what is the correct theory of physics, and I think it's fair to say that nobody knows. String theory is one of the most, or maybe the most popular approach, in the sense that it has the most people working on it, but there are also a lot of other very serious and interesting theories. Right now, none of these theories claim that they have really succeeded. Even string theory has a lot of open problems with it and so on, and it's a part of an ongoing journey for science to try to figure out what's really going on. But there is one thing which all of these candidate theories have in common, They're mathematical theories with equations which have more than one solution. And each solution corresponds to how things can be in a level 2 multiverse. And if inflation is true, then all of the solutions actually get realized and created for real. So that would, and then we simply find ourselves in sort of a typical one.
Yes.
So I think our basic argument for why we should believe in the level 2 multiverse, it comes as a prediction from inflation and also from the fact that any of these theories for how matter really works has many solutions. Even if string theory is wrong, I think we still probably have a level 2 multiverse.
Mm-hmm. So we can go to level 3 now. What is the scientific basis of level 3 parallel universes?
So the scientific basis there is quantum mechanics, which you alluded to when we talked about teleportation. When we've studied what everything is made out of, we find that my hand, for example, is made of molecules. The molecules are made of atoms. There are about 100 different kinds. The atoms are made out of only 3 particles, a ball of protons and neutrons with little electrons that orbit around them. And then we've discovered also that these protons and neutrons are made out of quarks, even smaller particles. And this is the theory of quantum mechanics is a very successful theory that describes how these particles work. And it's so successful that it's given us computers, cell phones, lasers, and so much of modern technology. But the theory also predicts some very surprising things. It turns out that these little particles don't behave the way we're used to big things behaving. This glass of water is either here or here. It can't be in both places at the same time, we think. But we've discovered that atoms can actually be in 2 places at once. We've made lots of experiments that demonstrate that. So this raises a deep puzzle. You know, if I'm made of particles that can be in 2 places at once, then I should be able to be in 2 places at once also. But why do I never experience this? And in 1957, there was a young student at Princeton University in America named Hugh Everett who came up with a very radical explanation for this. He said, actually, we can be in several places at once. It's just that if your brain if you are in 2 places at once, the way that will feel to you is as if there are now 2 different yous. There will be one Cristian Mureșanu who feels that he's over there, and another Cristian Mureșanu who feels that he's over there. And you can calculate mathematically that you will not be aware of each other at all. You will each feel that you are the only Cristian Mureșanu, and that's it. And this is the idea behind the level 3 parallel universes. You might think, oh, maybe it's possible in theory, but you're here in one place now. There is no mechanism that can ever put you in 2 places at once. But there is, actually. For example, if you make a quantum experiment, where some detector is either going to say yes or no, depending on the position of some little particle, then the particle could be in 2 places at once. So afterwards, the detector will say yes and no, and you can decide in advance that if it says yes, you're going to go over there. If it says no, you're going to go over there. So after you've done this, you will actually be in 2 places at once. And we've discovered that actually there are many, many processes like this. Even when we make decisions, for example, if I'm driving and I'm getting very irritated because there's a very slow truck in front of me. It's been there for 5 minutes and I'm very eager to pass the truck, but I'm a little bit afraid because it's a narrow road and there are cars coming. And then finally I think, now I have my chance, but I'm not sure I'm going to have time. And I make a snap decision and I'm like, yes, okay, I'm going to do it. Then that decision was very close, and it might have depended on just one little particle in my brain that entered some synapse, which caused some neurons to fire, which caused the cascade of other things, which caused me now so if the particle was in 2 places at once, then 1 second later, my whole car and me is either next to the truck or still behind the truck. Maybe I'll even get killed in one of these two universes and not the other. So in other words,
are these universes splitting every microsecond and create an infinite number of universes? Or?
So that depends on how we think about this. If we think of reality itself as just being this quantum world, which is governed by this equation of quantum mechanics called the Schrödinger equation, then there was only one world and there always is one world also. But this is not the world that we perceive. This is the world where everything can be in many places at once. What you can calculate, which you, Everett, did, is that the way it's going to feel to us is that like our reality is actually split. Because whenever I am in many places, each one of them, of the Maxes, will feel that they are the only one. So it actually feels to us as if there has been some kind of splitting. But the way it actually feels, of course, is not like, I never feel that I split. It just feels like something happens sort of at random. And we can understand this even without all this complicated stuff about quantum mechanics. So suppose we go into a hospital here in Cluj, okay? And some doctor there says that he can make a clone of you. So he scans where all of your atoms are exactly with this machine he's invented. And then first he gives you a sleeping pill, and then he tells you that when you wake up, in room 1, there will be the original you, and in room 2, there will be the perfect copy of you. But it'll be so perfect that when the copy wakes up, it will feel that it is also you. It has all the same memories, looks the same, and so on. So that means that so now I can ask you in advance, when you wake up and feel that you are you, which room will you be in? Will you be in room 1 or 2? You know that there will be somebody who feels that they're you who wakes up in both places, right? Suppose I go in the next morning and you've just woken up in room 2, the clone, and I tell you, hey, I'm going to bet you money. I'm going to bet you 100 lei that you're in room 1. What odds would you give me? You would say, well, I can give you 50-50. I could be the clone or I could be the original. There's no way to know. It's going to feel random to you. You can go out of the room and you can look at the number that's written and it says 2. It will look random. This had nothing to do with quantum mechanics at all, right? And the basic idea is just that if we get copied, if we get cloned, subjectively to us it will feel random. And this is actually a famous puzzle in quantum mechanics, that quantum mechanics has these measurements which have outcomes that seem random. It seems like there was no way we could have predicted what would happen.
But we cannot work with infinite solutions, because if an equation, which I understand from quantum mechanics, is giving me an infinite solution to that, I can't work with it.
But these things happen even if there's nothing infinite. Even if I only make 2 copies of you, it will feel subjectively random to you. So what you Everett said when he came up with this idea was that basically there is nothing really random in nature. But when things feel random, it's because we have been copied. And it turns out in the mathematical equations of quantum mechanics, it has the power to copy you in a sense, by taking your particles and putting them both here and there at the same time. This is, of course, very controversial. But basically, the higher the level of the multiverse you go to, the more controversial they are. But it's also very interesting because when you Everett first came out with this theory, people said, this is absolutely crazy, and they didn't want to give him a job in physics. But now people are very interested in this because of technology. You can use these ideas to build what you mentioned before, these quantum teleportation systems where you can send secret information from one bank to another using these ideas so that nobody can intercept the information. And people are trying very hard now also to build what's called quantum computers. They're computers where the whole calculation gets cloned in a way so that they can make parallel computations in all these parallel universes to get the answer faster. So your laptop has more than one processor in it, so it can do things quicker. And people are trying to build computers now which can calculate things much faster than even a normal computer the size of our universe could do. And they haven't succeeded yet with making big quantum computers, but if they do succeed in 10 years or 50 years, then I think people will take much more seriously these ideas. Because if the computer can get the answer so quickly by using calculations in parallel universes, you sort of have, it makes it more plausible, hard to deny that these things are sort of real.
But what I heard about the present moment which the technology arrived is molecular computers which are based on the level of an atom which can store an information by losing or accepting an electron, and this is the difference between the state of 0 and 1.
Yeah, that's right. And in fact, all of our computers, if you look inside how they work, they always encode zeros and ones somehow in the position, in the state of some atoms. Another very popular way of doing a quantum computer is, and you can have a particle that can be spinning either clockwise or anti-clockwise. This can be 1, this can be 0. And in the normal computer, each bit of information is either 0 or 1. So, for example, when we buy money on when you buy things on the internet, the codes that are involved there, to crack them, you have to be able to take a very large number, which is one big prime number times another, and figure out which two numbers were multiplied. The easiest way to check this is to say, well, can you take the big number? Is it divisible by 2? No. Can you divide it by 3? No. And you keep testing, but that takes a ridiculously long time because you have to try one at a time. But in a quantum computer, the bit of information, which depends on how the atom is spinning, cannot be just either 0 or 1. It can also be 0 and 1 at the same time. And if you take now many bits, which together maybe get interpreted as a number between, say, 1 and a trillion, this can now be all the numbers at the same time. And then the program can calculate with all the numbers at once in just one step, which is then trillions of times faster. This is, loosely speaking, one of the key ideas behind quantum computers. And so what we're seeing is that these ideas, which sound very crazy, now there's a lot of money in them and a lot of very serious experimental effort because
also
they're useful.
Quantum hard disk, because if the level of an atom can be used to be equal with a memory unit, which is so small, like the size of an atom, and you can create maybe 10,000 or millions of terabytes hard disk using atoms directly as the smallest memory unit.
That's right. We always want bigger and bigger hard disks, which means we have to make the bits themselves smaller and smaller, which means we approach the limit where there's 1 bit per atom when we have to deal with these quantum things. So the quantum world might seem very weird, but it's extremely useful. We've discovered recently also that nature takes advantage of this. For example, photosynthesis. It became clear that when a plant takes light from the sun and converts it into energy that it can use, it actually uses this quantum weirdness that particles can be in 2 places at once to do photosynthesis better. And if even plants can take advantage of this technology.
So this is why we cannot duplicate in industry the splitting the atoms from carbon and oxygen and combine because we need so much heat and power, and plants don't need that. So this is what you are suggesting?
Well, it's clear that nature has already taken advantage of some of these weird quantum effects to do things better and more efficiently. So I think we humans also should try to take advantage of it even more. In, for example, how we build our computers. And so I think basically it used to be that a lot of physicists were very angry about at Everett and said this is stupid and crazy, and now people are getting very interested because they're realizing it's actually useful, and they've sort of learned to love the weirdness.
Yes, and this is even more interesting about just a little bit to present a theory that in biology, in the human body, the cells are having 3 bytes behavior. It's 0, it's 1, and -1, because the cell can grow up, do nothing, or fall back. You know, this is and someone said that we may be creating in the future a 3 bytes computer.
Yeah, it's very interesting. We used to think that computers were limited by the laws of classical physics. They can be 0 and 1 and that's it. And people proved all these theorems and say you cannot crack this code, it's safe, because it would take more than 1 billion years to figure out what your password is and stuff. But now we realize those are not the true laws of physics. The actual true laws of physics are the laws of quantum physics, and they're different. And they let you do things which previously seemed impossible.
Also, quantum physics, and I wish to ask you your opinion about, said that if you observe a particle, then it behaves different than if you are not observing it, because it eludes the observation. It doesn't want to be observed.
Yeah, this is a key part of this mystery. So, if you can be in 2 places at once, or if this glass of water can be in 2 places at once, we have to explain why do we never see this. And it turns out you can prove by using the laws of quantum mechanics, and that there is a process, we call it decoherence. It was discovered in 1970 by a German physicist, Hans-Dieter Zeh, and there's a very nice book about it, actually co-authored, among others, with a Romanian physicist named Stamatescu also. And they showed that this decoherence effect causes a kind of censorship, that these quantum particles can only really be in 2 places at once in a useful way as long as it's secret. It only works as long as it's secret. As soon as somebody finds out...
So no observer is there, no
yes,
observer. Yes,
exactly. So as soon as any person or any part of the outside world finds out where this glass is, it destroys all these useful quantum effects. And this is why it's so difficult to build a quantum computer, actually, because you have to keep the whole calculation secret, not just from people, but from other atoms. If you have an atom which is here and here, and then a molecule of air comes and bounces off of one of them, now the atom found out what's going on, and the whole quantum calculation fails. So they have to take the quantum computers, maybe try to make them super cold, make it super vacuum, super dark. It's very difficult to try to keep the calculations secret. And the bigger the quantum computer is, the harder it is to keep everything secret. This is why you and I don't feel like quantum computers, because we are very big. And as we speak, millions and trillions of atoms are bouncing off of us. Particles of light bounce off of us, and that ruins any kind of attempt to keep secret from the universe what we're thinking about. So that's why when we think, we cannot use these quantum shortcuts. But that doesn't mean that we cannot build machines which are better at keeping the quantum secrets and do these very useful things.
Very fascinating. And let's talk now about level 4 of the universe.
So the 4th level of our multiverse, that's the most extreme and controversial kind, and I call it our the mathematical universe, or the mathematical multiverse. That's the main I talked about all 4 levels in this book, but that I just finished. But through climax of the book is
so the entire book is for explaining the 4th level.
But to understand the 4th level, first we have to understand everything about our universe that we talked about in the first program, which is the first part of the book. Then we have to understand the 1st level and the 2nd and the 3rd. So there are a lot of chapters about that. And then you get to the 4th. We talked before about where I work at MIT. A lot of students walk around with T-shirts with equations.
Yeah.
And we talked about, even if there is only, so the ultimate dream, of course, of theoretical physicists, like the ones working here across the street here in Cluj, is to find the correct equations, the theory of everything, which can describe all of physics. Maybe it's string theory, maybe it's going to turn out that that's wrong and it's something else. But suppose you have that t-shirt with those equations. Then you have to still ask, why those equations? Why not some other equations? Because in the math department here at Babeș-Bolyai University in Cluj, mathematicians study all sorts of other equations also. And you can classify all these different mathematical structures, as they're called, which are described by different mathematical equations. And you have to ask, of these equations, what's so special with the ones on the t-shirt that make them describe physical reality and not the others? And the idea behind the level 4 multiverse is to say that actually there is complete democracy. Each mathematical structure described by some equations that make sense actually corresponds to a real physical universe. So when we find out the equations that can give you the Nobel Prize in this universe that describe everything, string theory or whatever, that just tells us where we are in this bigger reality, because there is also another universe where some other equations hold. So if it turns out that string theory is wrong in our universe, there's another, but if it still makes sense as a mathematical theory, then there is a different level 4 universe where string theory is correct, where the string theorists can get the Nobel Prize. So this is the most diverse of all the kinds of universes, because every possible kind of physics actually happens.
I can't imagine this kind of level, because it's so complex compared to level 1 we have discussed earlier. How would life would be or exist?
It's very difficult to imagine. And first of all, life is probably impossible in most of these other level 4 universes. We have to remember, even in our own universe, within this region of space that we can see, life is actually impossible in most places. We live on an oasis, Earth, where things are just right. And on Venus, it's much too hot. On Mars, it's much too cold. And if we were to just teleport ourselves, like in the Stargate science fiction program you mentioned, to some random part of our universe, we would be in an intergalactic void, an empty space, an almost perfect vacuum. It would be so dark there that we couldn't see anything in any direction, and we certainly could not live there. So life is very fragile and only possible even in a small part of our universe. And I think in the multiverse, the fraction that can support life is even smaller. But that doesn't mean that this is the only kind of life that there can be. There probably are also other level 4 universes where
it's not carbon-based life, but silicon-based or something.
Yeah, maybe. We don't have, I think, enough imagination to imagine all possible kinds of life.
Yes,
but we can change now even very fundamental things. Like in our world, time flows smoothly like this. But if you play a computer game, an old computer game like Pac-Man, for example, time goes in discrete jumps like this.
Yes.
Right? You can imagine...
we are approaching the end of part 2. One more question. How does your knowledge about parallel universes affect your daily life?
That's a really interesting question. Sometimes I find it very difficult to reconcile how I feel with what I believe. For example, when Philip, my oldest son, was about to be born, I was a lot of time thinking, I hope everything is going to go well. But then I thought, maybe I'm being foolish, because if there are parallel universes, things will go well in some parallel universes and they will go badly in others. So what do I really mean when I say that I hope? Then I thought, well, maybe what I mean is I hope that I will be in in the parallel universe.
Universe which is
where things
go
go
well. Yeah.
But actually, that's also silly because they'll also be in the other universes because there'll be in a version of Max who's very happy and one who's not. So then I thought maybe what I mean is I hope that in most parallel universes things will go well. Maybe things will go well in 99.99% of all the universes at least. But then that's also really a little bit silly because the percentage of all the universes where Philip was born successfully and happily is something you can just calculate from mathematics. So how can you hope about that? So I think in the end maybe it's a good thing that I can't quite get my emotions fully linked with what I believe, and I think more importantly though, I think believing that reality is grander and bigger than we thought and different from how we thought, to me makes me more humble, and I think us humans having more humility is a very good thing. I think we are a little bit too arrogant often in how we go about dealing with our lives and with our planet, and thinking that reality is very different and very grand should make us more grateful for what we have and make us take better care of what we have and just really make the most of what we've been given.
Thank you very much. Thank you very much. And we'll continue our discussion next time.
Vom continua data viitoare, partea a treia.
Aceasta a fost partea a doua a discuției despre cosmologie, dar n-am avut timp suficient pentru o detaliere a ceea ce înseamnă multiversul de ordinul 4, și anume universul matematic despre care scrie profesorul MaxTegmark în cartea sa. O vom face data viitoare alături de alte completări, comentarii și precizări. Înainte de a încheia, doresc să vă anunț faptul că domnul profesor MaxTegmark vă stă la dispoziție pe pagina sa de Facebook cu orice întrebări legate de cosmologie și chestiuni discutate în cadrul emisiunii. Fiți alături de noi data viitoare la o nouă întâlnire cu știință și cunoaștere. Bun găsit la emisiunea Știință și Cunoaștere. Ne aflăm la cel de-al treilea și ultimul episod al întâlnirii noastre cu cosmologia, un subiect abordat în premieră la Știință și Cunoaștere, deoarece este extrem de delicat, chiar dificil de explicat pe înțelesul tuturor. Dar acest neajuns a fost înlăturat de modalitatea atractivă, simbolică și simplificată prin care domnul profesor MaxTegmark a abordat-o într-o discuție maraton de aproape 3 ore, pe care am reușit să o înregistrăm în luna august. Știința a progresat atât de mult în ultimii 20 de ani încât pur și simplu nu am fi capabili să o înțelegem dacă, simultan cu aceasta, nu s-ar fi pus bazele filozofiei legate de rezultatele științei. Multă lume a auzit, de exemplu, despre teoria relativității restrânse. O formulă ușor de reținut și înțeles pe care oricine și-o amintește. Aceasta este E egal mc pătrat, care ne dă energia echivalentă ce se obține atunci când un obiect de masă m ar atinge viteza luminii. Teoria unificată a mecanicii cuantice este un manual de peste 1800 de pagini. Ea nu poate fi redusă și înțeleasă de către oricine. Și atunci a apărut o formă de filozofie care comentează rezultatele fizicii cuantice prin percepte și concepte filozofice, unul din ele fiind prezența observatorului. Dar vom reveni asupra acestor subiecte și cu alte ocazii, așa că până atunci vă invit să-l ascultați pe profesorul MaxTegmark vorbind despre universul matematic. Hello and welcome, dear MaxTegmark, for the third time in our program Science and Knowledge here on TVR Cluj.
Mulțumesc foarte mult, mă bucur.
Și eu de asemenea. And we are now going to continue our talks about the mathematical universe hypothesis, and this is what we would like to explore in this program. So first of all, let me ask you, why math?
As a scientist, if I look back at all of the science that we humans have ever done, I think there are two ideas which have turned out to be incredibly useful. One idea is that we should do experiments, measure things. And the other is that when we measure things, we should try to make mathematical models for our measurements. Now, why has that turned out to be so useful? It's been incredibly useful to the point that Galileo exclaimed famously that our universe is a book, written in the language of mathematics. And that was 400 years ago. Since then, we've had enormous further progress of mathematical descriptions of gravity, of light, of how atoms work, and how gravity works, Einstein's relativity, and so on and so forth. And to the point that actually in the 1960s, the physicist Eugene Wigner wrote a famous essay where he talked about what he called the unreasonable effectiveness of mathematics in the physical sciences, and asked, why is this idea so powerful? Why is it so powerful to use mathematics to describe physics? And he felt that this is a question which really deserves an answer. Yet, so what is the answer? What I think the answer is, which is the key idea that my new book, Our Mathematical Universe, leads up to it, is that actually our universe seems so mathematical because it really is mathematical. And we'll talk more in great detail about what I mean by that. But if nature is at heart somehow completely mathematical, it's not so surprising that when we look more closely, we find these mathematical patterns.
So at the very core of the tiniest things we explore in our world and in the universe is the mathematic, not the matter itself?
Yeah, so that's a very good question. We look around in the universe, where is all this math that people talk about? I don't see any big numbers written out there in the sky. And yet, when we look more closely, there are actually a lot of very mathematical things just built into nature. I should say that, first of all, what is mathematics? To some people, mathematics is just a form of torture invented by teachers to make us feel bad about ourselves in school, or maybe a bag of tricks for manipulating numbers. But what mathematicians have gradually broadened the idea of mathematics to also include shapes and patterns and many other things. And what Galileo was talking about when he said our universe is so mathematical was particularly shapes and patterns. If I throw something and I look at the shape in which it moves, this shape, which we call a parabola, has a very simple mathematical equation. If you call the distance in this direction x, you call this y, the mathematical equation is basically y equals x squared. It's a very simple equation. And similarly, if you look with a telescope out into the sky and look at what shapes are the planets going around the sun, what shapes are stars going around the black hole in the middle of our galaxy, these shapes are all the same shape. They're all called ellipses. An ellipse is basically a circle a little bit squished. So this is an ellipse if you look at my ring from the side. So why are there all these shapes? We also have numbers, actual numbers built into nature. For example, if I ask how many pencils can I put that are all perpendicular to each other, the answer is 3, a number. We physicists have invented a name for this number. We call it the dimensionality of space. We say that space has 3 dimensions. But why is it 3, not 7 or 4? And when I weigh myself on a scale in the morning, I have a digital scale, so it also says a number. Maybe it says 87 kilograms. This number, you might think, is not really fundamental, because a kilogram, first of all, somebody else could weigh themselves and they would weigh something else, and the kilogram is something we invented, we humans. But if you take the weight of a proton and you divide by the weight of an electron, you get 1,836. And that number is really built into nature, because all protons weigh the same and all electrons weigh the same. And where do these numbers come from? We've discovered now, actually, that everything we've ever measured in physics we can calculate from just 32 numbers in principle, and then by doing certain calculations.
But let me also discuss this idea. We have, at least as I am guessing, or if I am correct, 3 levels of describing the universe. This is the matter level, which is very condensed, the energy level, which is less condensed but still measurable and visible, and the information level, which is maybe this is where everything is based on numbers and equations and the laws which make the energy level and the matter level in function. So the laws have had to be pre-existed before these 2 levels.
Yes, it does indeed seem as if these mathematical laws are in some sense more fundamental than the stuff that obeys the laws. And that is very much at the heart of what we'll be talking more about later in this program, and that the very fabric of reality in some sense is mathematical. That's right.
So now I am guessing very approach, because I am not specialized in this field, but this is how I thought it would be possible to understand the mathematical universe, which is something, a level within the deepest, the smallest level possible that we had explored until present, based on what we know about energy and particles, and this is much profound level.
I feel it's very profound and very exciting. That's why I'm so interested in this, because I've always been very curious about the biggest questions and what is the true nature of reality. So the more profound and fundamental it is, the more interested I become.
Yes. Have physicists discovered anything through mathematics? And can you give me some examples?
Yeah. So one of the most remarkable examples of the power of mathematics in nature is exactly what you mentioned here. When you can use mathematics alone just to discover something. Many things were discovered previously coincidentally. Somebody sailed to some place, discovered a new country, or somebody made an experiment and found a new effect. But if you ask about the planet Neptune, for example, or radio waves, or most recently the Higgs boson, all of those 3 things were actually discovered not with a telescope, not with a microscope, but with a pencil, doing mathematics. Neptune, what happened was people had discovered the planet Uranus after the telescope was invented, and they looked very carefully at how Uranus was orbiting around the sun, and it seemed like it almost obeyed Newton's laws of gravity, but not quite. Uranus was moving a little bit funny. So independently in France and England, 2 different guys had this idea that maybe it's moving funny because there is a new planet we haven't seen. And then they used mathematics and calculated to see what properties such a planet would have to have. And one of them actually wrote a letter to an astronomer in Berlin and said, on this day, at this particular time, you point your telescope to this particular place, you will there find a new planet. So this guy gets this, Gal was his name, this letter, and he probably thought, wow, this guy is cuckoo, this is ridiculous. But he was probably still pretty curious, so he took his telescope, he pointed it there, and boom, there is Neptune, a new planet, discovered ultimately with mathematics, with a pencil. And then history repeated itself many times. With radio waves, what happened was that James Clerk Maxwell had discovered these fantastic equations which described how electricity and magnetism work. And I mentioned in the last program that some of my students like to wear these equations on a t-shirt. So when he found these equations, he solved them. He realized that there was a new solution to his equations which corresponded to some kind of wave that could fly through vacuum, through empty space, very, very fast. And he calculated how fast it would go from his equations, and the answer he got was about 300,000 kilometers per second. And he thought, that sounds familiar, because that's how fast light travels.
Yes.
And he realized for the first time that light is actually also a kind of wave, an electromagnetic wave. And he realized that if light can travel through space, maybe we can also, with magnets and electricity, make our own waves, and that became called radio waves, and send them through empty space, and use that as a useful way of communicating with each other. This was all done with mathematics, just theory. Later on, scientists like Hertz actually built devices where they were able to actually show, wow, this works. And as a result, we now have our cell phones and the information society that we live in. And it was all predicted, again, with mathematics. And the most recent example that I want to give is the Higgs particle. Peter Higgs,
yes,
took all of the latest and greatest knowledge we had about particle physics and studied the equations and realized that for it to all really make sense, he needed to introduce some more stuff in one of the equations. And he predicted that if you built the biggest and most elaborate machine that humans have ever built, the Large Hadron Collider in Geneva, and if you collided particles together there near the speed of light in a certain way, and you measured very carefully, you would there discover a new particle, the Higgs boson. As you know, the machine was built, and there it was. And it was predicted by mathematics.
So the Higgs boson is real, after all?
Well, for many years, this was just a theory. But now, thanks to the fantastic work of physicists from around the world, including many Romanian physicists at the Large Hadron Collider at CERN, we found it. It's there. And this is another great triumph, I feel, for mathematics as a powerful tool for discovering things about our universe.
Yes, and but also there was an incident regarding that at a certain experiment had been found some particle which could travel more than the speed of light. Can you tell me about?
Yeah, there were a lot of there were some particles which were discovered. They had made measurements, and it seemed like they made it a little bit faster than the speed of light, which would have violated the mathematical equations of Einstein's theory of relativity. And then eventually other people measured this more and more carefully, and it turned out the measurement was wrong. They had actually made a mistake. So the mathematics was correct, and the people were wrong.
So we are not yet above the speed of light.
No, and this is another example, again, of how powerful these mathematical equations are. It's truly really remarkable how well these equations and formulas have worked in describing our world.
In what sense do you believe the universe is mathematical?
Yeah, so that's a very deep question that you're asking now, because on one hand, yes, there are properties of the universe which correspond to numbers, but it seems like there are a lot of properties which are not mathematical. Like, I don't know, do you have a cat, for example?
No.
So if somebody, maybe one of the viewers has a cat and looks at this cat, and you ask, okay, what properties does this cat have? Maybe it's cute, has the property of being cute. Maybe it has the property of being fluffy. Maybe it's a little bit shy, a little bit mischievous. They don't feel like mathematical properties, right?
Yeah.
Yet we know that cat is actually made of elementary particles, such as quarks and electrons. And what properties does an electron have? Well, it has the property -1, 1/2, 1, and so on. Now, we scientists have fancy names for these particles. properties. We call them the electric charge, the spin, and the lepton number, but those are just words that we made up. The only properties that the electron actually has are numbers, mathematical properties. So the electron itself is a purely mathematical object in the sense that it actually has no properties at all beyond mathematical properties. You can't say that the electron itself is cute or fluffy or shy. It just has these properties like -1.
Well, these are concepts based on our emotional reactions to things.
Yeah, exactly. So we humans, when we see complicated things made of these particles, assign other properties to them too. But the basic building blocks of matter, all of the different kind of particles are purely mathematical in the sense that they have no properties at all except various numbers, mathematical properties. So you might ask, okay, maybe the stuff in space is mathematical, but surely not space itself. So what properties does space have? Well, we already talked about one such property, the property 3, right, the dimensionality. That's also mathematical. And mathematicians have also discovered other properties that space has called curvature and topology, which are important in Einstein's theories.
Quantization of space.
When we add quantum mechanics too, but if we look at classical space, it has these other properties like curvature and topology. They are also, it turns out, purely mathematical properties. Here in the Cluj, in the math department at Babiš-Bolyai University, they study curvature and topology and dimensionality. So actually, space itself, as far as we know, has no is a purely mathematical structure in that it has no properties at all other than mathematical properties. So now, if space itself is mathematical and the stuff in space is mathematical, then it doesn't sound as crazy anymore, the idea that maybe everything is purely mathematical. And that's exactly the mathematical universe hypothesis that I talked about in this book, that that we are simply part of this vast mathematical object, our universe. And the reason that we can approximately describe it by mathematics is because sometimes some complicated mathematics can be approximately described by some simpler mathematics. For example, if I have a sheet of paper which is approximately flat, you can write down some very complicated equation for this surface. You can approximately describe it as a flat piece of paper, which is simpler. And we humans discover these simpler approximations first, and gradually, as our physics research gets better, we discover more and more accurate approximations to the true mathematics. But the hope is that one day we can discover the actual correct mathematical equations which describe our world.
How much of them are discoveries and how much of them are invented?
So this is a wonderful controversy, actually, not just among us physicists, but also among mathematicians. Is mathematics something which is discovered, or is it something which is invented? I believe that there is an external physical reality that's out there, independent of us. So even if MaxTegmark, didn't exist, there would still be a reality out there. And when I, as a scientist, study it, I believe I'm discovering what's out there. I'm not inventing it. But not everybody agrees. There are solipsists who believe that nobody except them exists. And they're entitled to believe that. There are also much more serious physicists, like, for example, Niels Bohr, a founding father of quantum physics, who we discussed, who said things like, no reality without observation. So he would not necessarily accept this idea that the reality is independent. There is a reality independent of us. He felt that observation and us humans are, very central. But I believe that we should be more humble and accept that that the Andromeda galaxy exists independently of us, and we discover these physical things. And what about mathematics? Well, it's very interesting. I have many friends who are mathematicians, and they usually also say that they discover things about mathematics. They don't invent them. For example, Plato was very interested in geometric shapes over 2,000 years ago, and discovered that there are exactly 5 kind of really regular 3-dimensional shapes that are now called Platonic solids. The cube, which we all know, and then a tetrahedron, and then the octahedron, which is made of 8 triangles, an icosahedron with 20 triangles, and a dodecahedron. And those are the only 5 that you can ever make, which are completely irregular. And when he felt that he discovered the existence of the dodecahedron, he didn't feel that he invented it. He felt that it sort of was there, this mathematical structure, the idea of this perfect shape.
Maybe it's a combination between what we discover and it is valid and verifiable in all cases, and in sometimes we use equations, for example, adding and extracting the same number in order to create a better condition to solve the equation.
Yeah, that's a very nice example. So mathematicians, when they study different mathematical structures, they include not only shapes like the cube, but also things like numbers. The simplest kind of numbers are the ones we call the integers, 0, 1, 2, 3, 4, and so on. And if you look at the numbers, I think almost no mathematicians would say that they invent the fact that 5 plus 2 equals 7. You can discover that it's 7 by making the calculation. And the universe, it feels like reality had no choice. You can't have mathematics where 5 plus 2 equals 8. It's inconsistent. And but what we can discover are useful tricks and methods for how to manipulate the numbers.
So they are invented.
Well, I'm trying to just give you a flavor of the range of opinions that people have. I mean, a lot of computer scientists would also say that then the algorithm, the method, we also discover. And it couldn't have been in the most, we learn in school a way of multiplying numbers, which is an algorithm, and there's an even more effective, faster one that computers use. And then there is one that you can prove that is the fastest, sort of, and the computer scientists would say that, again, these are also things we discover the methods. And if it's true that nature itself is a mathematical object, then this feeling that mathematicians have that they discover mathematics, and the feeling that we physicists have that we discover the Andromeda galaxy, we discover Neptune, are one and the same feeling of discovery. We learn more about what actually exists out there. And that's how I think it is. I firmly believe that we don't invent mathematics, we discover it. What we invent, it's very interesting that you asked this, what we do invent, though, are the names for the numbers. In the number 3, for example, in Romanian we don't say 3, we say tre. In Swedish we say tre. In German we say drei. Those are inventions. Right?
Oh,
each culture invents its own name for the idea of 3, but it's still the same number, no matter what we call it. If you have a Spanish mathematician who says cinco más dos igual a siete, and an English mathematician who says 5 plus 2 equals 7, it's the same truth, because you can have a dictionary that says if you translate each of the words, the claim of one mathematician is the same as the other person's claim. Similarly, the way we write the numbers, we've invented. You know, in Western Europe, and in fact all of Europe, we write the number 3 like this, and so on. But in India, they write the numbers differently.
The language in which we communicate the science. This has been invented.
This we invent. We invent the symbols, the words, the notation, but the basic structure is exactly the part which remains when you strip away all the baggage that we have invented.
Yes, but this is very useful because if we want to transmit knowledge, for example, someone is discovering something in Japan, and if he is using the common words which are translatable and understandable for all of us, then his knowledge can be shared to everyone.
That's right.
But
that's right.
If someone is discovering something which is very weird and is using too much symbolistic language and with no clarity of creating good explanation, then he would not be understood, but only by other people who share the same thinking method.
Exactly. So language is very useful, which is why we humans invent it. But we have to remember, nonetheless, that it was we who invented it. And this would become particularly urgent. Suppose in the future we were able to make contact with a civilization somewhere else in space. They won't share any of our language. Then we have to work very hard to establish some form of communication. And when you explain to a computer how to calculate something, again, you have to get rid of all the human words because the computer doesn't understand Romanian, and only look at the abstract mathematical structure, which is what's left when you take away the language. And this is also very important in physics because we have, if you take the basic equations of mathematics that describe our world, like we talked about in the last two programs, and you solve them, you find, oh, there is a solution to these equations that corresponds to a bunch of quarks and electrons that form a very stable object here. And then you find that there are many of these in different places in space. Then it becomes very convenient to invent a name for this object. So we call it atom. And then you work some more on the equations, and you find that sometimes you get 10 to the power 57 atoms that clump together in a big ball in space that shines off energy. And then we realize, oh, when we solve the equations, you have many of these. Then it becomes convenient again to invent a word for that. We call it a star. So it's very good that we invent these words, but it is still we humans who invent the words. If you were, in principle, a very, very talented mathematician could, by just studying the equations, figure out that there are stars and all the properties of our world without using our language. And in this sense, it's actually possible to describe things purely mathematical.
Yes. However, our world keeps changing, but mathematical structures don't. So how can they be the same?
Now that's a very important and subtle question. For example, the abstract cube is just this object which always has 6 faces, always has had 6 faces, always will. There's nothing that changes about the cube. Whereas our world, things are happening. How can those two be the same? Well, Einstein taught us a very interesting lesson about this. Einstein said that there are 2 different equivalent ways of looking at our physical reality. We can either think of reality as being this 3-dimensional place where stuff happens over time, where there's change. Or we can think of reality as being a 4-dimensional place where time is just the 4th dimension and nothing ever happens. And he called this way of thinking about it space-time. So if we think of our life as a movie, then space-time is the entire DVD. And there are 2 different ways you can think about the DVD. You can play it, and then you think of things as happening, but you can also just look at the DVD itself. It's a static, unchanging object, and encoded in this DVD is a grand drama with people, with things beginning and people falling in love and problems and so on, and then ending. But the DVD itself is not changing. So this is Einstein's way of thinking about the physical world as this 4-dimensional reality that contains the full story. And it is that Einstein 4-dimensional reality which is a mathematical object.
Is the theory of quantization of space and time more still valid or not? Is time and space have really the smallest quantum time ever possible to exist, and also the smallest length the universe is capable of, or they are invented too?
So you just asked the most embarrassing question facing physics today, which is it's very important that we put on the table, because the truth is we have these 2 very successful theories in physics. We have Einstein's theory of general relativity, which describes all the big things in our universe, and gravity, and it works very, very well. And then we have this other theory of quantum mechanics, which we talked about in the last program when we talked about the level 3 multiverse, which describes small things and atoms and how computers and cell phones and other technology works. Also very successful. But these two theories don't really like each other. And we have still, to this day, failed to find a mathematical set of equations which combines the two of them to everybody's satisfaction. And this is the... If you can figure out how to do that, I can guarantee you will get a free trip to visit my hometown of Stockholm and collect your Nobel Prize in physics. Because it's the most embarrassing, outstanding problem for theoretical physics. What I think we can also say, though, is that there are many different approaches that try to unify quantum physics with gravity. We don't know yet which one of them is right, if any. But all of the different candidate theories that are competing are all completely mathematical again. So there is really no indication that the conclusions we were drawing about things being mathematical will change. String theory, for example, the most popular attempt, is an extremely mathematical theory. It's so mathematical, in fact, that Ed Witten, one of the most famous string theory pioneers, got the Fields Medal, which is like the Nobel Prize, not in physics, but in mathematics. So it seems like whatever the true theory turns out to be, it's very likely it's purely mathematical.
It will also have some philosophical consequences. If, for example, the time and space would be quantized, then that means they would have just like an oscillating signal, rectangular signal. This is 1, and the other semi-period is 0 or non-existent. So if time is quantized, then it had to be a series of 0 and 1, 0, 1, 0, 1, which means at 1, when it is 1, a Planck time, all the universe is here with everything as we see. On the next Planck time, the universe is gone, and this is nothing.
Well, you're asking exactly the kind of questions now where you need a unified theory of quantum mechanics and gravity to give an answer. What happens when you look at things that are so small that you need quantum mechanics, but also so heavy that you need gravity? And we can't answer them because we don't have that theory yet. I think what's safe to say, though, is that, the sort of space that we have now and the time that we think intuitively we understand is probably only an approximation to something deeper.
Yes.
Just like we talked about how an approximately flat surface can be approximated by being perfectly flat. That's simpler math. The true nature of space and time is probably different, but approximately like this. Even the air in the room that lets you hear me now because of the sound waves feels like it's very continuous in a smooth medium, right? And we can write down equations for how the waves move, which makes the assumption that you can divide space into infinitely many little pieces. We know that's wrong because we know that actually the air is made of atoms. There's only a finite number of atoms. And the only reason that the air feels smooth, I blow like this, is because there's so many atoms. The atoms are so close together and so small that it averages out to something very, very smooth. And in the same way, it's quite possible that the space between us also is made of some fundamental building block that's not smooth and continuous, and that it's only because
fundamental geometrical building blocks.
Yes, exactly. Yes. There might very well be some fundamental geometric building blocks, maybe of some quantum nature. The physicist John Wheeler, for example, speculated that maybe if you look at space, if you could zoom down and stretch things out so that everything gets 10 times bigger, and then you do that 34 times in a row, you would see what he called quantum foam, that space becomes really fuzzy. And we have good reason to think it doesn't even make sense to talk about any distances that are smaller than 10 to the power minus 34 meters, because our whole idea of space probably breaks down. But nonetheless, these questions which string theory and other approaches are trying to tackle all have in common the idea that it's all mathematical. It's different mathematics then, maybe with different geometric concepts that are the building blocks, but it's still mathematical at heart. And this is, again, this basic idea I'm talking about, how it seems like like the basic fabric of reality is mathematical.
Please tell us more about your book.
Sure, yeah. So, as you can probably tell, I'm very excited about these ideas, and I have been very excited about them for a good part of my life. And I wanted to share some of this excitement with a broader audience in a way that's easy for any intelligent and interested person to understand, even if they haven't spent any time at all studying physics in school. So this book is both my attempt to explain some of these exciting ideas and also a bit of my personal journey. I divided it into several different parts. So the first part of the book talks about all the great discoveries we've had in cosmology, our first program basically, and how we've learned more and more about how big our universe is and parallel universes and such. The second part of the book talks about instead the question, what is everything made of? When you look to smaller and smaller scales, quantum mechanics and all these fascinating things we talked about in the last program, and the level 3 parallel universes. And then the third part of the book, I talk about what we've discussed here today, how it's so mathematical and what that means, and how that even gives evidence of a still bigger level 4 multiverse. And I should also say the subtitle of this book, which is available now on Amazon for pre-order, and anyone who's interested in talking with me about the book also is very welcome to visit my Facebook page. You can ask questions and I'll be delighted to answer. It's Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. So this book, even though it's mainly not about me, but about our universe, it's sort of through my eyes. I talk a lot here about my own experiences and adventures and misadventures, you know, the disappointments when things have gone wrong in our work, and the excitement that I've had the good fortune to be part of. And I hope also that the person who reads this book will come away with more of an appreciation for how exciting our universe is and how fun it is to be part of this detective story to try to figure out more about how our reality works. So another interesting implication, if this is true, that our universe really is completely mathematical, then you can make an argument, which I make in the book, that the level 4 multiverse that we talked about last time actually exists, so that our reality is even bigger. Even if string theory turns out to be wrong here in our universe, there is another universe where string theory is correct. So it, in a way, gives us the grandest possible reality. And I think that if it turns out that I'm wrong, that means that our universe, that our quest for knowledge and understanding will eventually hit a roadblock beyond which we can't proceed, because things are not mathematical anymore, and we humans, no matter how hard we try, just can't understand and predict things. But if it turns out that I'm right, then I think that's very exciting, because then there is no roadblock. And we can continue our quest to understand our reality better and better, and we're only limited by our own imagination.
So there is no such things like the end of science, which a writer predicted in his book, The End of Science, you know, I don't recall his name.
Well, if I'm right, then there will not be an end of science, because we hit that roadblock where things are no longer mathematical. The only thing, there might be an end of our imagination and creativity, but I think that's always been the challenge for artists and poets also, to become more creative and imaginative. And that's what I very much hope for, that we will have this, that it will be up to us if we have enough imagination to continue figuring things out.
Also, and I don't know how much time we have, there is an interesting theory which I found about, promoted by Michael Talbot, the holographic universe. Is the universe really holographic?
We don't know. The holographic principle is an idea which is a key part of one of the approaches to quantum gravity and unifying gravitation and quantum mechanics. We don't know yet whether it's ultimately going to be correct or not. I think it's very important in a situation like this where we don't know what the right answer is, that we pursue all different ideas that are out there. And because if everybody is just doing the same thing, we're much less likely to have one of us actually find the truth. So even if it turns out to not be correct, we should definitely study it.
How this information can help us get a better life for ourselves.
Sure.
In order to, for example, to apply some philosophical concepts, philosophical theories in our life. For example, if quantum mechanics said, if you are observing a certain very intimate phenomenon, then that phenomenon is changing. If you observe a particle, the particle is behaving like a wave. If you are observing a wave, the wave is behaving like a particle. And for example, some biologists said that if you are doing this kind of observation, of a conscious observation through your body, you can change your physiological parameters of the body, just to observe them. And you can observe, you can change them. So they want to apply what they call the quantum biology, but it is not quantic. It's not just taking the philosophical concept and to apply in a real phenomenon, to do real changing.
So that's one out of many examples we can give of how using mathematical equations to understand our reality better, we can develop powerful new technologies. And I think to bring this back to home and ask, what does this mean for us humans on this planet and for us personally? It's very important to maybe look at all of these three programs and discussions we've had and say, what have we sort of learned? And this gives a different perspective. For me as a cosmologist, my perspective is that there's this small little ball in space, our Earth. There's 7 billion of us living on there. And in this vast universe, we've learned that life is very rare, and we're very fortunate to be on such a habitable, life-friendly planet. And we've also learned that we have these fantastic technologies that can do wonderful things for us, and technologies which can destroy us. So I feel that as a species, life has reached the fork in the road where we have to really make a choice. Either we will take the path of death and destruction, and because for the first time in the history of our universe, there's a species that actually has the technology to destroy itself. Or we can get our act together and build something truly remarkable and wonderful together, and maybe in the future, in the distant future, life can spread from our planet out into our universe. Maybe one day our entire universe can come alive. And I think, as we talked about in the first program, we are not at all insignificant, because we might be the only planet in our universe which has this technology. And we are also not insignificant, even though our lives are short. You know, if we eat our vitamins and exercise, maybe we can live for 100 years. But our universe is 14 billion years. It might feel short. But this period right now in our lifetime might be when the big fork in the road happens, when we have to decide whether we can get more organized as a species and focus on what's really important, or whether we self-destruct. So I think, again, for the viewers out here, especially children and teenagers who are thinking about what to do with their careers, you should feel very empowered and realize that what you do here on this planet in your lifetime, what you choose to study, how you choose to change society, can change not just the course of life in Cluj or in Transylvania, or on Earth, but for our entire observable universe. It's amazing. And so I think the more we appreciate this perspective, I think the better our chances that the future of our universe will be a worthy one.
Well, I thank you so much for this meeting, and have such a nice talks in these three programs. And I hope that we can meet at least once per year, every year, Are you going to visit Romania next year in 2014?
Mi place foarte mult Transilvania, and I of course love my family here in Cluj, so I think it's safe to say that we'll be back many times, and it's been a real pleasure. Mulțumesc foarte mult!
Mulțumesc și eu și mi-a plăcut să avem această conversație și aș vrea să o continuăm atunci anul viitor cu ocazia unei noi întâlniri.
Foarte bine!
A treia parte a discuțiilor a fost mai scurtă, cu 9 minute, așa că am profitat de promisiunea profesorului de la Facultatea de Chimie, Adrian Pătruț, de a reîncepe să participe la știință și cunoaștere. Și l-am invitat să ne spună câteva concluzii legate de cele 3 părți ale interviului cu profesorul MaxTegmark, cosmolog de talie internațională la Institutul de Tehnologie din Massachusetts, Statele Unite. Adrian, mă bucur că ne întâlnim din nou la știință și cunoaștere. Tu ai o viziune largă asupra științelor și ai participat la emisiuni foarte diversificate ca domenii și ne bucurăm să te avem din nou alături.
Pentru mine emisiunea aceasta cu MaxTegmark a fost o surpriză foarte plăcută, fiindcă, dacă îți amintești, de multe ori ți-am spus că este necesar să facem emisiuni despre cosmologie, care sunt complicate. Ai găsit un om de primă mărime, pe plan mondial, care ți-a dat niște interviuri, le putem comenta, ne putem adresa publicului larg, putem face un dialog și este un mare succes. Mai înseamnă că este încă o temă importantă pe care trebuie să o dezbatem și să o găsim, problema aceasta a evoluției omului, care este astăzi în dezbateri foarte interesante, sunt noi descoperiri și care merită să fie studiate, sunt punctele tare ale cercetării științifice. Tegmark a avut un articol de referință în 2004, în februarie, în Scientific American, în care a descris cele 4 tipuri de lumi paralele, unele care sunt foarte asemănătoare cu ale noastre, altele mai puțin asemănătoare, în care putem avea un alter ego, în unele dintre ele, în altele nu. Aceste lumi nu prea pot comunica între ele, sunt situații speciale aici. Aici este problema de a crede sau de a nu crede. Este foarte greu de adus dovezi în favoarea lor. Există anumite elemente pentru care anumiți psihologi preferă astăzi, anumiți fizicieni preferă astăzi, în loc cu interpretarea Copenhaga clasice a mecanicii cuantice, acea interpretare a universurilor multiple a lui Evans și Everett, care este interesantă și care spune, de exemplu, că eu, dacă vin, de exemplu, la studio pentru un interviu, atunci eu pot să vin cu grosier cu autobusul 30, pot să vin cu taxi sau cu autobusul 28 și lumea se scindează în 3 și eu apar în 3 lumi diferite și evoluez diferit în fiecare dintre ele în funcție de opțiunea mea și la fiecare acțiune pe care o am eu și fiecare alt om și fiecare altă ființă și până la particule microfizice, universul se scindează în atâtea universuri câte probabilități există. Toate acestea evoluează independent și paralel. Deci sunt universuri în care noi nu existăm, altele în care am existat, dar avem un destin diferit, în care ne-am născut în alt moment, în care nu ne-am murit deja, în altele ne vom naște, în unele suntem probabil preoți, în altele suntem oameni de știință, etc., etc. Deci este o teorie foarte interesantă, foarte greu de demonstrat, dar care, datorită unor observații cosmologice de astăzi, referitoare la galaxii îndepărtate, la quasari și la roiuri de galaxii mai ales, sunt preferate de către unii cosmologi față de teoria clasică, cea de la Copenhaga, care spune că se alege o singură probabilitate, pisica Schrödinger și așa mai departe, colapsul vectorial al funcției de undă și că tot timpul se face o selecție și că noi avem, ca și observatori conștienți, posibilitatea de a influența tot timpul realitatea fizică. Deci nu suntem observatori doar, ci suntem și participanți în această lume. Și că universul este chemat la manifestare și se alege opțiune care este oferită tocmai de mintea noastră, care face această selecție în momentul observației. Deci această observație este esențial. În teoriile celelalte, în teoriile de universului multiple, practic tot timpul are loc. Universul se divide în N universuri în funcție de probabilități existente și nu mai există această acțiune directă a observatorului în momentul observației.
Și cu ce viteză se divide el, dacă se divide? Se divide
la fiecare eveniment cuantic, acum am avut
fiecare secundă, microsecundă.
Am avut o observație aici, un caz macrofizic, dar practic aceasta se petrece la nivel microfizic. De câte ori particulă microfizică se spune că este emisă și poate trece prin 3 fante, universul se scindează în 3. Într-unul trece prin fanta A, în altul prin fanta B, în altul prin fanta C. Da? Și aceasta se întâmplă de N ori în fiecare fracțiune de secundă. Există astăzi peste 10 la 80 de universuri paralele care evoluă independent. Și fiecare o istorie proprie, ele nu pot comunica între ele, deocamdată credem, și o poveste fascinantă, așa un fel de multivers și deodată lumea este mult mai bogată decât credem noi și toate visele sunt posibile, unde toate iluziile sunt reale, nu? Deci istorii sunt complet diferite.
Da, da, aici mai este un element. În momentul în care ezoteriștii au auzit teoria asta în care totul devine posibil, au luat și au implementat-o în modul în care totul devine posibil, dar aici în lumea noastră.
Bine, acum...
Deci,
acum povestea...
Și încep să creadă din nou în acele lucruri care n-au nicio legătură cu lumea noastră.
Da, acum întotdeauna curentele ezoterice, acele care vin de la Blavatsky încoace, trecând prin mișcarea teozofică, prin Alice Bailey și așa mai departe, prin toate povestile acestea interesante, prin Charles Leadbeater, prin Annie Besant, au încercat să găsească descoperiri științifice care să justifice teoriile lor. De exemplu, atunci când a apărut radioactivitatea, s-a spus că radioactivitatea aceasta, descoperită de Becquerel și confirmată pe urmă de către Irena Skłodowska, ulterior Madame Curie, practic eu am spus că radioactivitatea aceasta este domeniul eteric și poate astral și cum emite atom astral soarele și ce frecvență au ei, și a spus că în sfârșit au descoperit aceasta ezoterică ascunsă oamenii de știință. Până au văzut că nu este, s-a mers tot felul de descoperiri științifice care au încercat să fie exploatate de către toți cei care susțin doctrine mai puțin ortodoxe în punct de vedere științific în favoarea lor. Deci întotdeauna când va fi o descoperire științifică, se va spune că aceasta confirmă teoria noastră, până când se va vedea că o infirmă și va fi o altă descoperire științifică și mai departe. Deci întotdeauna spuneam cândva că cele mai bune profeții sunt cele care se fac după ce evenimentul s-a împlinit. Da? Cum este cu sfârșitul lumii, că n-a fost în 2012, că va fi în 2022 sau în 2013 sau ceva, întotdeauna a trecut momentul și spune nu, că s-a greșit, va fi peste 10 ani. Și așteptarea aceasta trebuie să fie menținută. Trebuie să ai un număr...
Există o nouă dată a sfârșitului lumii?
Evident.
Care?
S-a spus cu 2022-2023. Deci totdeauna există noi date pentru că există o masă de credincioși acolo care te susțin, ai un cerc de adoratori undeva care susțin aceste mișcări ezoterice și care trebuie să nu fie dezamăgiți niciodată. Păi, domnule, da, s-a greșit acolo, o interpretare greșită, cu tare, dar o așteptăm din nou și va veni. Deci nu trebuie să omori speranța.
O lovitură mare acum cu 2012.
O lovitură mare a fost faptul că că media și foarte multe instituții care trebuie să fie bine informate au crezut în așa ceva. Inclusiv oamenii de știință care au făcut niște profeții înspăimântătoare, care nu știu ce s-a întâmplat cu ei și în România și în alte țări. Deci au mușcat aici, să spunem, la această nadă care este cu mileniarismul, cu sfârșitul lumii, care e de nu știu când povestea aceasta. Nu are o tradiție de peste 1000 de ani. Deci, totuși, undeva și noi făceam emisiuni și undeva ascultătorii erau dezamăgiți când spuneam că nu va fi. Deci chiar dacă oamenii doresc să trăiască clipe dramatice, au nevoie de adrenalină, care le creează senzații deosebite și așa mai departe și se gândesc cu oroare, dar și cu un oarecare orgasm, între ghilimele, spun în cel puțin intelectual, dacă nu fizic, la anumite evenimente dramatice care ar putea aștepta și cu care ar putea fi contemporani, chiar dacă acestea i-ar afecta. Și mulți au fost dezamăgiți că nu s-a întâmplat nimic îngrozitor care să strice acest echilibru.
Păi, dar nici măcar o calamitate naturală n-a venit în 2012, cum a fost în 2004, și care anul 2004 nu era nicăieri pe nicio listă profetică că ar urma să se întâmple ceva. Și deci 2012 a fost chiar un an liniștit, fără războaie, fără nicio bombă atomică, fără furtuni deosebite, uraganul Katrina și altele.
Da, sigur. Deci... Da, dar vezi că lumea a devenit în esență tot mai puțin culturală, mai puțin științifică în ultimii ani, pentru că oamenii sunt interesați nu de aflarea adevărului, ci de căutarea profitului. Foarte mulți, inclusiv în România, unde, de exemplu, nivelul învățământului a scăzut dramatic față de acum 20 de ani și a cunoașterii la nivel de masă. Și atunci oamenii sunt tentați să aibă astfel de... să creadă în lucruri foarte simple și foarte naive de multe ori. Deci acest adevăr științific este foarte complicat ca să fie înțeles de către omul obișnuit care nu are o pregătire suficientă în fizică, nici în alte, în cosmologie, să explici lui de ce este necesară evoluția umană, pentru că practic, sau evoluția biologică, fiindcă aceasta este doar o etapă în evoluția întregul univers ca și ansamblu, de la Big Bang încoace, că tot universul practic se află într-o evoluție, nu? Că este o problemă foarte mare aici și de ce este necesară evoluția? Fiindcă practic universul are o anumită energie inițială, mă rog, foarte mare și această densitate de energie scade în timp prin expansiune și atunci trebuie undeva să fie compensat. Deci ca universul să poată evolua, atunci se creează ansamble din ce în ce mai mari, care sunt tot mai sărace în energie și ele pun în libertate energie și universul poate evolua în continuare, nu? Se obțin din particule simple, particule compozite, se obțin nuclee, se obțin atomi, se obțin molecule, se obțin molecule mai complexe și se tot pune, se eliberează energie care permite universul să evolueze în continuare. Deci evoluția este un factor necesar și obligatoriu în universul ca el să existe.
Mulțumesc foarte mult, Adrian, și atunci te așteptăm cât de curând.
Și eu mulțumesc.
Aici s-a încheiat și ultima parte a seriei dedicată cosmologiei, singura știință care îndrăznește să caute răspunsurile la marile întrebări existențiale și la neliniștile noastre metafizice. Și religia încearcă să facă aceasta. Nu e nicio concurență între cele două, ci probabil că e o completare, însă de pe poziții foarte diferite. Înainte de a încheia, doresc să vă reamintesc din nou faptul că domnul profesor MaxTegmark vă stă la dispoziție pe pagina sa de Facebook cu orice întrebări legate de cosmologie și chestiuni discutate în cadrul emisiunii. Fiți alături de noi data viitoare la o nouă întâlnire cu știință și cunoaștere.